The universe is full of innumerable stars and even more planets, many of which are in the habitable zone, where life, as we know it, can prosper. This leads us to a profound question posed by the physicist Enrio Ferri. Where is everyone? If life is so abundant, why haven't we detected any indication of extraterrestrial civilizations? The paradox of Ferri essentially highlights the contradiction between the high probability that extraterrestrial civilizations exist and the lack of evidence detected any indication of extraterrestrial civilizations. The paradox of Ferri essentially highlights the contradiction between the high probability that extraterrestrial civilizations exist and the lack of evidence of contact with them. Our Milky Way alone contains more than 100,000 million stars, many of which harbor planets in their habitable zones. Given the age of the galaxy and the number of potentially habitable planets, it seems statistically probable that intelligent life has emerged elsewhere, yet we observe silence. This silence raises questions about the conditions necessary for life and, more specifically, for intelligent life. One possible explanation for the paradox of Ferri is that the conditions necessary for life, especially intelligent life, are much stricter than we have assumed. The appearance and maintenance of complex life may depend on a series of rare and interdependent conditions. In this documentary, we will explore how plate tectonics influences the capacity of the planets to harbor and maintain life. We will examine the unique geological characteristics of the Earth, compare them with those of our neighboring planets, and discuss the implications for the search for extraterrestrial life. By understanding the fundamental role of geology and habitability, we may discover that the rarity of plate tectonics is a significant factor in the Fermi paradox. One of them is its dynamic geology driven by plate tectonics. But what exactly is plate tectonics, and why is it so crucial for life? Plate tectonics refers to the movement of large plates that make up Earth's surface. These movements create mountains, cause earthquakes, and play a vital role in regulating the planet's climate by recycling carbon through volcanic activity. Plate tectonics is a fundamental aspect of Earth's geology that involves the large-scale movement of 7 main plates and numerous minor plates that float on the semi-fluid asthenosphere below the lithosphere. This process is responsible for many geological phenomena, such as earthquakes, volcanic activity, the formation of mountains, and oceanic trenches. The concept of plate tectonics revolutionized our understanding of the dynamic nature of the Earth and its ability to sustain life. In addition, plate tectonics contributes to the recycling of essential nutrients, such as phosphorus and potassium, which are vital for life. The constant renewal of the planet's surface through tectonic processes ensures that nutrients are continuously recycled and available to living organisms. Without this renewal, the life system that provides us with nutrients will be trapped in rocks and sediments, making the planet less habitable. On a larger scale, plate tectonics also creates diverse and complex habitats. The formation of mountains, islands, and oceanic basins through tectonic activity generates a variety of ecological niches that promote biodiversity. These diverse habitats offer opportunities for different life forms to evolve and adapt, leading to the rich tapestry of life we see today on Earth. However, the presence of plate tectonics is not a given on all planets. Tectonic activity is driven by internal heat generated by radioactive decay and residual heat from its formation. This heat creates convection currents in the mantle that drive the movement of tectonic plates. For a planet to have tectonic plates, it must possess sufficient internal heat and a composition that allows the formation and movement of lithospheric plates. The presence of tectonic plates on Earth may be a rare and fortunate phenomenon. If tectonic plates are essential for the development and maintenance of complex life, planets without tectonic activity would be less conducive to harboring advanced civilizations. This rarity could help explain why we have not yet detected signs of extraterrestrial life, despite the large number of potentially habitable planets in the galaxy. To understand the uniqueness of the Earth, we must compare it with its planetary neighbors, Venus and Mars. Despite being in the habitable zone, neither has tectonic plates. Venus, with its dense toxic atmosphere and extreme surface temperatures, has a stagnant lid, which means that it is crossed as a single moving piece. Mars, smaller and colder, lacks the internal heat necessary to drive tectonic activity. Venus, often referred to as the sister of the Earth due to its similar size and proximity, presents a marked contrast in terms of geological activity. Despite its potential habitability in the past, Venus currently presents a tectonic regime of stagnant lid, which means that its lithosphere does not break into mobile parts, but remains as a single rigid layer. The lack of tectonic activity on Venus is attributed to its extreme surface conditions, with temperatures reaching approximately 900 degrees Fahrenheit and a dense atmosphere composed mainly of carbon dioxide. These conditions prevent the formation of the thermal gradients and convection currents necessary in the mantle that drive plate tectonics. Mars, on the other hand, offers a different perspective on planetary tectonics. Mars is smaller than Earth, with only a third of its size and a colder internal structure. These factors contribute to the absence of active plate tectonics on Mars. The surface of the planet shows evidence of volcanic activity and tectonic features of the past, such as the enormous volcano Olympus Mons and the canyon system Valles Marineris. However, these characteristics are believed to be vestiges of a past era in which Mars was more geologically active. Today, the lack of significant internal heat and a thinner atmosphere limit the tectonic and volcanic activity of Mars, making it a geologically dead planet. Geologically dead. The absence of plate tectonics on Venus and Mars has profound implications for their habitability. Without plate tectonics, these planets lack the mechanisms for long-term climate regulation and nutrient recycling. On Earth, the carbon cycle driven by plate tectonics helps stabilize climate over geological time, creating a stable environment for life to thrive. In contrast, the stagnant lid of Venus leads to an uncontrolled greenhouse effect, while the active geology of Mars gives rise to a cold and arid landscape. The absence of plate tectonics on Venus and Mars suggests that the geological conditions to sustain complex life are uncommon. If other potentially habitable planets in the galaxy also lack tectonic activity, they may be less conducive to advanced civilizations. The scarcity of geologically active planets could be a factor in explaining the cosmos' apparent silence. Earth was not always so geologically active. It initially had a stagnant layer like Venus, but over billions of years, the increase in internal heat and tectonic stresses caused the crust to fracture into plates. This transition to active plate tectonics coincided with the emergence of complex life, suggesting a profound connection between the geology of the Earth and biological evolution. The Earth was a very different place from the planet we know today. In its beginnings, the surface of the Earth was dominated by a stagnant layer similar to the one we observe today in Venus. This meant that the lithosphere was a single, uninterrupted layer with minimal tectonic activity. However, as the planet cooled and internal heat accumulated, the lithosphere began breaking into plates. This transition marked the beginning of plate tectonics as we understand it. The change from a stagnant lid to active plate tectonics was a gradual process driven by several factors. One of the most important was the accumulation of internal heat from radioactive decay and residual heat from the. This heat created convection currents in the mantle that exerted pressure on the lithosphere above. Over time, these stresses caused the lithosphere to crack and form distinct plates that could move independently. Another crucial factor in the development of plate tectonics was the presence of water. Water acts as a lubricant, reducing the viscosity of the mantle and facilitating the movement of tectonic plates. The presence of large oceans on Earth likely played a role in the formation and movement of plates. Water also contributes to the weakening of the lithosphere by promoting the formation of subduction zones, where one tectonic plate is pushed below another, driving the recycling of the lithosphere into the mantle. The timing of the transition to active plate tectonics is closely related to the appearance of complex life on Earth. Geological evidence suggests that significant tectonic activity began about 3 billion years ago, roughly coinciding with multicellular organisms' emergence. This correlation suggests that the development of plate tectonics may have created the conditions necessary for the evolution of complex life. The Drake equation is a formula used to estimate the number of advanced civilizations in the galaxy. Traditionally, it includes factors such as star formation rates and the probability of planetary formation. By incorporating geological factors, we can refine these estimates. Planets with active plate tectonics could be rare, making complex life even less common than previously thought. The Drake equation, formulated by astronomer Frank Drake in 1961, seeks to quantify the number of technologically advanced civilizations in the Milky Way that we could contact. The equation takes into account several factors, including the rate of star formation, the fraction of stars with planetary systems, the number of planets per star that could harbor life, the fraction of planets on which life actually develops, the fraction of planets with intelligent life, the fraction of civilizations that develop detectable technologies, and the time that these civilizations emit detectable signals into space. Traditionally, the Drake equation focuses on astronomical and biological factors, assuming that life's development is mainly influenced by the availability of suitable conditions, such as liquid water, appropriate temperatures, and a stable atmosphere. However, recent research suggests that geological factors, particularly plate tectonics presence, play a crucial role in creating and maintaining habitable conditions. By integrating geological considerations into the Drake equation, we can gain a more nuanced understanding of the likelihood of finding advanced civilizations. One of the key geological factors to consider is plate tectonics' role in regulating a planet's climate. The carbon cycle driven by tectonic activity helps stabilize atmospheric carbon dioxide levels and maintain a relatively stable climate over geological time. Without this regulatory mechanism, a planet's climate could become too extreme for complex life to thrive. By incorporating active plate tectonics presence into the Drake equation, we can refine our estimates of the number of planets that maintain stable, habitable climates. Another important consideration is the recycling of nutrients through tectonic processes. The constant renewal of the planet's surface ensures that essential nutrients remain available to living organisms. Planets without active tectonics may lack the nutrient cycle necessary to sustain complex ecosystems, limiting the potential for advanced life forms development. Including nutrient recycling as a factor in the Drake equation allows for a more accurate assessment of a planet's ability to sustain complex life. The creation of diverse habitats through tectonic activity also plays a role in promoting biodiversity and evolutionary innovation. The formation of mountains, islands, and ocean basins generates a variety of ecological niches that provide opportunities for different life forms to evolve and adapt. This diversity is crucial for the long-term sustainability of complex ecosystems and the development of advanced civilizations. By considering tectonics' role in creating diverse habitats, we can better estimate the number of planets with the potential to harbor complex life. The incorporation of geological factors into the Drake equation highlights the rarity of planets with the right conditions to sustain complex life. If active plate tectonics is essential for maintaining habitable conditions, then the number of planets capable of harboring advanced civilizations could be far smaller than previously thought. This rarity could help explain the apparent silence of the cosmos and provide a solution to the Fermi paradox. Scientists are now looking for exoplanets that show signs of plate tectonics. Missions such as the James Webb Space Telescope and others aim to detect signs of geological activity on distant worlds by analyzing the atmospheres and surfaces of exoplanets. The researchers hope to identify planets with the potential to harbor complex life. The search for exoplanets featuring active geological processes is a rapidly advancing field, driven by new technologies and innovative observation techniques. The discovery of planets orbiting stars outside our solar system has opened exciting possibilities for finding habitable worlds. To date, thousands have been identified, and a significant number of them are in the habitable zone of their parent stars, where conditions could be suitable for the existence of liquid water. One of the main challenges in identifying exoplanets with plate tectonics is detecting geological activity at great distances. Traditional exoplanet detection methods, such as the transit method and radial velocity measurements, provide information about the size, mass, and orbit of the planet, but offer limited data about its biological characteristics. To overcome this challenge, scientists are developing new techniques to analyze the atmospheres and surfaces of exoplanets, seeking signs of tectonic activity. The telescope size, the mass, and the orbit, but offer limited information about its biological characteristics. To overcome this challenge, scientists are developing new techniques to analyze the atmospheres and surfaces of exoplanets in search of signs of tectonic activity. The James Webb Space Telescope, JWST, represents a major advance in our ability to study exoplanets. Equipped with advanced instruments capable of analyzing the composition of exoplanetary atmospheres, the JWST will look for signs of gases associated with geological processes, such as the emission of volcanic gases, the detection of certain gases, such as sulfur dioxide and carbon dioxide, in the atmosphere of an exoplanet could indicate active volcanism and tectonic activity. Another promising approach involves studying the thermal emissions of exoplanets. Planets with active tectonics and volcanic activity emit heat that can be detected through infrared observations. By analyzing the thermal signatures of exoplanets, scientists can identify those with higher surface temperatures, indicative of geological processes. This method, combined with atmospheric analysis, provides a complete picture of an exoplanet's geological activity. In addition to direct observations, researchers are also using computer simulations and models to predict the likelihood of plate tectonics occurring on exoplanets, introducing data on the size, composition, and orbital characteristics of a planet. Scientists can simulate its internal dynamics and assess the potential for tectonic activity. These models help prioritize targets for observation campaigns and refine our understanding of the conditions necessary for plate tectonics. The search for exoplanets with plate tectonics is not limited to current missions. Future space telescopes, such as the European Space Agency's Ariel mission and NASA's Habitable Exoplanet Observatory, HABEX, are designed to provide even more detailed observations of exoplanet atmospheres and surfaces. These will build on the capabilities of the JWST, allowing more accurate measurements of geological activity and the identification of habitable exoplanets. The detection of exoplanets with active plate tectonics would be an important milestone in the search for extraterrestrial life, as these planets would likely have a stable climate, nutrient recycling, and diverse habitats, increasing the chances of finding complex life forms. The identification of these planets would also provide valuable targets for future missions aimed at direct imaging and characterization of exoplanetary surfaces. In the context of the heat paradox, the search for exoplanets with plate tectonics addresses one of the key factors that may influence the development of advanced civilizations. If the presence of active geological processes is rare, it could help explain the apparent scarcity of intelligent life in the galaxy. Focusing our search on planets with the right geological conditions, we increase our chances of finding habitable worlds and potentially answering the profound question of whether we are alone in the universe. As we continue our search for extraterrestrial life, understanding the role of geological activity becomes increasingly crucial. The geological solution to the FMY paradox suggests that complex life requires specific and uncommon conditions. Future discoveries will depend on our ability to find planets with the right geological characteristics. The search for extraterrestrial life is one of the most profound scientific projects of our time. It challenges our understanding of the universe and our place in it. As we explore the cosmos, we must consider the fundamental role that geological processes play in creating and maintaining habitable conditions. The geological solution to the Ferry paradox provides a compelling framework for understanding why advanced civilizations may be rare. The future of the search for extraterrestrial life will involve a multidisciplinary approach that combines knowledge from astronomy, geology, biology, and planetary science. Advanced space telescopes, such as the James Webb Space Telescope, and future missions such as Ariel and Havoc, will provide unprecedented capabilities for studying exoplanets. These instruments will help us detect and analyze the geological and atmospheric conditions of distant worlds. Scientists are looking for signs of tectonic activity and other indicators of habitability. The discovery of exoplanets with active plate tectonics would revolutionize our understanding of planetary habitability. These planets are likely to have stable climates, diverse ecosystems, and the conditions necessary for complex life to thrive. The identification of these planets would provide valuable targets for future missions aimed at direct imaging and in-depth characterization of exoplanet surfaces and atmospheres. In addition to observation missions, the search for extraterrestrial life will benefit from advances in computational modeling and simulations. By refining our models of planetary formation, evolution, and geological processes, we will be better able to predict which exoplanets are likely to have active tectonics. These models will help guide our observation efforts, allowing us to prioritize our most promising targets for the future. International collaboration will be essential for advancing the search for extraterrestrial life. Coordinating efforts between space agencies, research institutions, and scientists from various disciplines will enhance our ability to explore the cosmos. By sharing data, resources, and expertise, we can accelerate the pace of discovery and increase our chances of finding evidence of life beyond Earth. The potential discovery of extraterrestrial civilizations would have profound implications for humanity. It would challenge our understanding of biology, technology, and our place in the universe. The search for extraterrestrial life is not just a scientific search. It is a search for answers to fundamental questions about existence, intelligence, and our place in the cosmos. The geological solution to the Fermi's paradox suggests that the conditions necessary to sustain complex life are more stringent than previously assumed. The presence of plate tectonics, with its associated benefits for climate regulation, nutrient recycling, and habitat diversity, may be a key factor in determining the habitability of a planet as we continue to explore the cosmos. Understanding the importance of geological processes will be crucial to guiding our search for extraterrestrial life. The future of this search promises groundbreaking discoveries that will redefine our understanding of the universe and our place in it. Have you ever heard of a galaxy that defies any classification? Imagine a cosmic structure that combines an inactive ancient nucleus with a bright halo of young stars. It is not a typical spiral or elliptical galaxy, but something far more mysterious. A Hogg object, initially mistaken for a planetary nebula or a gravitational lens. The true nature of the Hogg object remained hidden until more advanced observations revealed its unique structure. The central elliptical nucleus appears red and inactive, while the outer ring is bright blue and full of new star formation. A clear separation divides the two components, as if they belong to different galaxies. The object has an impressive extension of 121,000 light-years wide, with a central nucleus of about 17,000 light-years in diameter and an outer ring that extends 75,000 light-years. This apparent separation between the nucleus and the ring is wider than the ring itself, a surprising characteristic for such a colossal galaxy. Ring galaxies like the Hogg object are extremely rare, making up less than 1% of all galaxies. They often arise from complex cosmic events, but Hogg-type objects seem to maintain a calm and orderly appearance, which further deepens the mystery. Despite decades of research, astronomers are still debating the origin of this galaxy. Was it the result of a quiet accretion process, or did a cosmic collision have something to do with it? Arthur Hogg, a prominent astronomer of the mid-20th century, made a discovery that would intrigue and baffle scientists for decades. In 1950, while conducting a study of the night sky, the astronomer came across a celestial object that defied conventional classification. This object, which was later named after him, had characteristics unlike any previously observed galaxy. At first glance, the Hogg object appeared to be a planetary nebula, a cloud of gas and dust surrounding a dying star. However, its unusual structure, formed by a central nucleus surrounded by a luminous ring, suggested otherwise. The first images taken by the astronomer's telescope showed a clear separation between the internal and external components, which aroused curiosity and speculation. The initial hypotheses varied greatly. Hogg himself suggested that it could be a planetary nebula or even a gravitational lens. The gravitational lens hypothesis suggested that the object was not a galaxy, but a huge elliptical galaxy that magnified a background galaxy into the form of a ring. Gravitational lenses occur when a massive object, such as an elliptical galaxy, deflects light from a more distant object located behind it. This curvature creates a ring of light around the foreground object, known as an Einstein ring. In the first observations, the outer ring of the Hogg object resembled such a lens, suggesting that it could be a foreground galaxy amplifying the light from a more distant object. For almost 4 decades, the true nature of the Hogg object remained uncertain. It was not until 1987 when astronomers, equipped with more advanced technology, were able to confirm the connection between the ring and the nucleus through spectroscopic analysis of the redshift. This redshift is due to the expansion of the universe, as more distant objects exhibit a greater redshift. By analyzing the redshift of the nucleus and ring of the Hogg object, astronomers confirmed that they are not separate entities, but components of the same galaxy. This discovery disproved the gravitational lens hypothesis and consolidated the status of the Hogg object as a unique type of galaxy. The central nucleus, formed by old red stars, contrasts sharply with the outer ring, which is bright blue and actively forming new stars. It is this special composition and structure that distinguishes the Hogg object from the Hogg object from typical spiral and elliptical galaxies. Ring galaxies are rare and make up less than 1% of all known galaxies. Typical spiral galaxies have arms of stars that extend outward, while elliptical galaxies have a more uniform and rounded shape. The Hogg object, with its perfectly separated nucleus and ring, remains one of the best defined examples of this rare class of galaxies. The discovery initiated a scientific journey to understand one of the most mysterious structures in the universe. With the help of modern telescopes and ongoing research, astronomers are trying to unravel the mysteries surrounding this fascinating cosmic anomaly. Its calm appearance, the combination of an ancient nucleus with a young star-forming ring, make the Hogg object a unique and enigmatic galaxy that has led astronomers to investigate various theories about its origin and evolution. Thus, one of the main theories proposed to explain the formation of the Hogg object is the collision hypothesis. According to this theory, the characteristic ring structure of the galaxy arose as a result of a high-speed collision between a smaller and a larger galaxy. When a smaller galaxy collides with a larger one, the impact generates a density wave that expands outward from the center of the larger galaxy. This wave compresses the interstellar gas, causing the formation of stars in the ring that surrounds the nucleus of the galaxy. The Cartwheel Galaxy, with its strikingly similar ring structure, is a classic example of this process. In the case of the Hogg object, if a smaller galaxy collided with it, one would expect to detect several key characteristics. First, the collision would create density waves that would push the gas and stars outward, forming a ring. In addition, the stars in the ring should have shown high relative velocities, indicating the kinetic energy of the collision. And third, in or near the ring, there would be residual fragments or remnants of the colliding galaxies. However, detailed observations of the Hogg object have revealed some inconsistencies with the collision hypothesis. The stars in the ring do not show the high relative velocities that are usually associated with this type of event. In addition, there is a total absence of residual fragments or evidence of a second galaxy. To test this hypothesis, models of galactic collisions have been used. These models show that, although a collision can produce a ring structure, the resulting galaxy often retains traces of a violent interaction. The Hogg object, with its calm and symmetrical appearance, lacks these chaotic characteristics, suggesting a more complex formation history. However, another intriguing possibility looms: the resonance theory. Could the ring structure of a galaxy be the result of gravitational interactions within a spiral galaxy? Let's explore this question. Another fascinating theory that explains the formation of the Hogg object is the resonance theory. According to this theory, the ring structure of a galaxy can arise as a result of internal dynamics in barred spiral galaxies. In particular, spiral galaxies are characterized by the structure of a central bar, from whose end spiral arms branch off due to the resonance in the gravitational field. These bars play a key role in the dynamics and evolution of galaxies. According to the theory, as the bar rotates, it can create a resonance that affects the distribution of gas and stars within the galaxy. Resonance occurs when gravitational forces within a galaxy create regions where rotational speeds of stars and gas synchronize. These regions can trap gas and stars, which leads to ring formation. There are several basic types of resonances. The internal Lindblad resonance occurs near the center of a galaxy and often forms an inner ring. The external Lindblad resonance occurs further away and can form an outer ring. The third type is the corotation resonance, a region in which the rotation speed of the bar coincides with the orbital speed of the stars and gas, which can also lead to the formation of rings. In the case of the Hogg object, the presence of a ring around the elliptical nucleus suggests that these resonances may have played a role in its formation. The bar structure could have caused resonance that trapped gas and stars at certain radii, creating the distinctive ring we observe. When the bar rotates, it exerts gravitational influence that can reorganize the galaxy's gas and stars over time. This process can lead to formation of a well-defined ring structure. The resonance theory provides a mechanism explaining how a spiral galaxy can evolve into a ring galaxy without collisions. NGC 1291 is a classic example of a galaxy in which resonance effects likely played a role in the formation of the ring. The central band and outer ring provide a visual analogy of what may have happened in the Hogg object. However, the resonance theory faces difficulties when applied to the Hogg object. In particular, the Hogg object does not currently have a central bar. This absence raises the question of whether the bar may have existed in the past and subsequently dissipated, or whether other processes may have contributed to the formation of the ring. However, there is another interesting and equally plausible theory, the accretion theory. Can the gradual accumulation of intergalactic gas explain the galaxy's unique structure? Let's explore this in more detail. The third important theory proposed to explain the formation of the Hogg object is the accretion theory. According to this theory, the unique structure of the galaxy is the result of the gradual accumulation of intergalactic gas, rather than a dramatic collision or an internal resonance. Accretion is the process by which a galaxy collects gas over a long period of time from the surrounding intergalactic medium. This gas is dragged by gravitational attraction, gradually accumulating and forming new structures. In the case of the Hogg object, a central elliptical nucleus likely formed first over time. The gravity of this nucleus attracted gas from the intergalactic medium, and as the gas approached the nucleus, it began to rotate around it, forming a ring structure due to conservation of angular momentum. As the gas accumulated in the ring, its density reached a level high enough to trigger star formation. This process explains the bright blue color of the ring, which indicates ongoing active star formation, and the space between the nucleus and the ring is explained by the balance of gravitational forces. The dynamics of falling galaxies, such as NGC 6028, are an example of how accretion can lead to the formation of ring structures. These galaxies show similar characteristics: older central nuclei and younger rings of star-forming regions, which supports the accretion theory as a plausible explanation. While the accretion theory offers a plausible explanation, it also raises questions. Why does the ring form at a specific radius? How do the dynamics of gas inflow and star formation create such a clear separation between the nucleus and the ring? These questions continue to drive research and exploration. Continued observations have provided evidence supporting this theory. The Hogue object contains more gaseous mass than the entire Milky Way, suggesting significant accretion of intergalactic material. In addition, the well-defined structure of the ring and the absence of chaotic debris are consistent with a gradual, orderly accretion process. Recent research has also significantly deepened this theory by modeling the gravitational interaction in such ring systems. Scientists have demonstrated how the balance of forces can create stable and unstable orbits that lead to discontinuities in matter distribution. These results are consistent with the observed structure of the Hogue object, where the space between the nucleus and the ring is a region of unstable circular orbits, further supporting the theory. In addition, the accretion theory offers a fairly compelling explanation for the formation, suggesting that the galaxy grew and evolved through the slow accumulation of surrounding gas. This process contrasts with the more violent and destructive events described in the collision and resonance theories. However, each of these proposed theories, collision, resonance, and accretion, has its own flaws, leaving several unanswered questions. Although the collision hypothesis explains the formation of the ring by density waves created by galactic collisions, it does not explain the ordered structure of the object, the absence of residual fragments, or the high relative velocities that are commonly observed in such events. The resonance theory, on the other hand, suggests that internal gravitational resonances within a twisted spiral galaxy can create ring-shaped structures. However, the Hogue object clearly lacks the central bar necessary for this process, and the theory does not fully explain the apparent space between the nucleus and the ring. The accretion theory, for its part, argues that the gradual accumulation of intergalactic gas forms a ring. While this explains the ordered structure and ongoing star formation, questions arise as to why the ring forms at a particular radius and how the dynamics between the nucleus and the ring create such a distinctive space. Despite these theories, several mysteries remain. Why is there a significant space between the nucleus and the ring? What specific conditions led to the formation of such a well-defined structure? And how do gravitational forces and dynamics interact within the galaxy to maintain this equilibrium? Future telescopic missions, such as the Nancy Grace Roman Space Telescope and the extremely large telescope to be launched soon, are designed to provide a deeper understanding of these issues. These advanced observatories will provide higher resolution images and more detailed spectroscopic data that could reveal the processes underlying the formation of this type of ring galaxies as we explore the cosmos. The Hogue object continues to be a testament to the diverse and complex processes that form galaxies and reminds us again that there are still mysteries to discover in the cosmos. Are we alone? This question is in a certain way as old as the light of the stars that travels through the eons to reach us. Since the first civilizations, our ancestors have looked at the night sky with amazement, with the imagination ignited by the flickering lights that were seen above their heads. Today, armed with the power of science and modern technology, we continue to wait for the answer to this ancient question. But our objective is not only to find primitive life, but to discover the whispers of civilizations that could share this great cosmic stage with us. The Breakthrough Listen Project, the most ambitious search for these whispers, technological signals, is expanding the limits of our hearing in an attempt to capture the murmurs of extraterrestrial life. At this crossroads of discovery, several teams of scientists from the Breakthrough Listen study and other SETI projects have already published scientific articles that bring us closer to answering this question. So, how close are we to the goal in this great search? What important decisions have been made to guarantee a fluid search for signals and improve our possibilities? Let's get to the bottom of the matter in our celestial odyssey to unravel the mysteries of life beyond Earth. Scientists have traced two main paths through the cosmic seas: the search for biosignatures and for technological signatures. Each path offers a unique lens through which to view the potential for life in the universe. Guided by astrobiology and the advanced technologies at our disposal, biosignatures, the chemical footprints of life, serve as beacons in our search for biological activity on distant worlds. These signatures are not only markers, but signs of complex interactions between living organisms and their environment. Each molecule, from the oxygen and ozone created by photosynthetic life forms to the methane and carbon dioxide produced by biological and geological processes, carries with it a story of potential life. The James Webb Space Telescope, JWST, with its unprecedented sensitivity to the infrared spectrum, is our most advanced explorer in this endeavor. Through transmission spectroscopy, the JWST can analyze and dissect the light from distant stars as it passes through the atmospheres. This light carries the traces of various molecules, each of which absorbs certain wavelengths and leaves a spectral signature that the JWST can detect and analyze. By observing the depths of space, the JWST searches for these spectral lines with precision, allowing us to infer the presence of water vapor, carbon dioxide, methane, and other potential biosignatures in the atmospheres of exoplanets. This method not only points to the possibility of life, but also provides information about the atmospheric composition, climate, and habitability of these distant worlds. Parallel to the search for biosignatures, the presence of technosignatures, the footprints of technologically advanced civilizations, is sought. Unlike biosignatures, which indicate the presence of life in any form, technosignatures suggest a leap towards complexity, in which life has evolved to use and manipulate its environment in profound ways, from radio signals to megastructures orbiting distant stars. Technosignatures embody the potential to detect not only life, but also societies that may have mastered the art of cosmic communication. The search for technological signatures extends throughout the galaxy. Initiatives such as the Breakthrough Listen project use vast networks of radio telescopes to listen for signals that travel through space. These telescopes scan the sky in search of narrowband radio signals, anomalies in the natural cosmic radio that could indicate deliberate transmissions from intelligent beings. Biosignatures are whispers of life embedded in the fabric of a planet's atmosphere that allow a glimpse into invisible worlds orbiting distant stars. Among the large number of possible biosignatures stand out for their importance: oxygen and ozone, phosphine and ammonia, methane and carbon dioxide, and mysterious unexpected combinations of molecules. Oxygen, the breath of life on our planet, and its companion, ozone, form the first pair of key biosignatures. Oxygen is a byproduct of photosynthesis, the process that formed our atmosphere and allowed life to thrive. The presence of ozone, a molecule formed from oxygen by ultraviolet radiation from the sun, provides a protective layer that shields the surface from harmful radiation. The discovery of these molecules in the atmosphere of an exoplanet could indicate the presence of a thriving biosphere, perhaps similar to our own. Phosphine and ammonia, less common but no less intriguing, represent a second pair of biosignatures. Phosphine, a gas associated with anaerobic ecosystems on Earth, has been proposed as a possible marker of biological activity on other planets. Ammonia, another molecule with biological links, may indicate the presence of life, especially in environments where it is not expected to exist in significant quantities due to non-biological processes. Methane and carbon dioxide form the third cornerstone of our quartet of biosignatures. Methane, a potent greenhouse gas, can be produced both biologically by organisms such as methanogens and abiotically by geological processes. Carbon dioxide, a critical component of the Earth's carbon cycle, is a product of respiration and volcanic activity. The simultaneous presence of methane and carbon dioxide, especially in unexpected proportions, may indicate biological processes. Finally, with the fourth point, we enter the realm of unexpected combinations of molecules. Methane and carbon dioxide cannot be stably present in large quantities simultaneously without transforming into other substances. Such combinations challenge conventional expectations and point to the possibility of life based on alien biochemical processes. The James Webb Space Telescope, JWST, the most advanced observatory of the most advanced observatory of humanity, is designed to study the atmospheres of exoplanets in search of these same B signatures. Through transmission spectroscopy, the JWST studies the light of a star as it passes through a planet's atmosphere during its transit. When light passes through atmospheric gases, certain wavelengths are absorbed by the molecules, leaving a spectral footprint that the JWST can detect and analyze. On the other hand, technological signatures, the footprints of advanced civilizations, offer a different path in our search not only for life, but for societies that have reached a level of technological sophistication similar to, or even superior to our own. Unlike biological signatures, which indicate only the presence of life, technological signatures speak of the ability of civilizations to alter their environment on a large scale, communicate through the stars, and harness energy in ways that we are only beginning to imagine. Technological signatures encompass a wide range of signals and structures, from radio waves emitted unintentionally by a planet's communication networks to deliberate beacons aimed at the stars, from colossal energy collectors known as Dyson spheres to the barely perceptible glow of city lights on the night side of an exoplanet. If detected, these signals will not only indicate the presence of life, but also provide detailed information about the technological capabilities of alien civilizations. Our own planet is a perfect example of a world full of technological signals. Each radio emission, each satellite, and each piece of space debris orbiting Earth creates a symphony of signals that, to a distant observer, would undoubtedly indicate the presence of an advanced civilization. The very structure of our daily life, from global communications networks to space probes heading towards the unknown, generates a cascade of signals that radiate into space, making our presence known to all who can hear us. But why are technological signatures a more accurate way to search for technologically advanced civilizations? The answer lies in their specificity and in the intentional or meaningful nature of the signals and structures they represent. Biosignatures can come from simple microbial life forms or complex ecosystems, but technological signatures clearly indicate a level of technological development and intent. The discovery of a technological signature not only confirms the existence of life, but also indicates that this life has crossed a threshold of cognitive and technological capacity, participating in activities that leave an indelible mark on the cosmic canvas. Breakthrough Listen was launched in 2016 with the ambitious mission of scanning the cosmos in search of signals from technologically advanced civilizations. The project represents one of the most exhaustive searches for alien technological signals ever undertaken. Armed with cutting-edge technology and unprecedented reach, the project uses some of the world's most powerful radio telescopes, including the Green Bank Telescope and the Parkes Observatory. These colossal ears, tuned to the silent whispers of the universe, can detect a wide range of signals, from faint radio emissions from distant stars to potential transmissions of extraterrestrial origin. The main objective of the mission is to detect technological signatures, that is, signals that, by their nature, can only be produced by technological means. These can range from narrowband radio signals that differ from the natural background noise of space to powerful laser pulses that cut through cosmic noise. The project had previously focused on the Milky Way for strategic reasons, to begin the search in our cosmic neighborhood, where these signals may be stronger and more detectable. The Milky Way, with its billions of stars, provides fertile ground for this work. Each observable star is a potential sun for other planets, and each planet is a potential cradle for life, as we know it, or for life yet to be imagined. The project was originally designed not only to search for signals in our galaxy, but to explore the nature of life and intelligence in the universe. Examining the cosmic immensity of the Milky Way in search of signs of life is like looking for a single whispered word in a bustling metropolis. A galaxy of about 100 billion stars can easily hide the signals of other civilizations. The task of monitoring such a wide range of targets for technological signals is monumental, not only because of the large number of stars, but also because of the complex variety of cosmic phenomena that can obscure the signals we are looking for. The problem is compounded by the limitations of our current technology and the limited resources available. Even with the most advanced radio telescopes, we can only listen to a small fraction of the stars in the galaxy at any given time. The enormous distances dilute the signals, making them weaker as the light years pass, and various natural cosmic phenomena, such as the emission of pulsars and nebulas, add complexity to the search. Faced with these challenges, astronomers and scientists have looked beyond the familiar limits of the Milky Way towards the wider universe, observing galaxies as individual entities, each composed of billions of stars. We could try to capture the accumulated signals of advanced civilizations. This extragalactic strategy is based on the premise that a sufficiently advanced civilization can harness technologies that affect its entire galaxy, from the construction of megastructures such as Dyson spheres to the harnessing of energy from supermassive black holes. Such grandiose undertakings could lead to signatures that, in theory, could be found in vast intergalactic voids. The transition to extragalactic studies poses some challenges, from even greater distances to the need for more sensitive instruments and sophisticated methods of data analysis. However, each galaxy observed and each data set analyzed brings us closer to understanding whether we are truly alone in the universe or whether we are part of a grander galactic community. Extragalactic exploration is precisely what Carmen Chosa and her team did in 2023 using the Robert C. Byrd Green Bank Telescope. The team has embarked on an ambitious mission to observe the centers of 97 nearby galaxies and study them for 5 years. This work, one of the largest of its kind, uses the search for narrowband Doppler drift in 4 frequency bands from 1 to 11 gigahertz. The goal was to detect signals that could come from civilizations capable of using energy equivalent to that of a Kardashev Type II civilization. The most important aspect of this study was the implementation of the Turbo SETI pipeline, a sophisticated tool designed to search for Doppler drift. This pipeline played a crucial role in analyzing the vast amount of data collected during the study to combat the persistent problem of radio frequency interference, called RFI, which often mimics extraterrestrial signals. The team adopted an on-source, off-source cadence pattern. This method consists of alternating between observations of a target galaxy at the source and a nearby region devoid of the target source, and is repeated 3 times for each galaxy, since radio frequency interference and localized noise are present regardless of the orientation of the telescope and appear in both on-source and off-source observations. In contrast, a true astronomical signal should only manifest itself in the observations of the source and not in the observations beyond the source. This approach helped to distinguish real astronomical signals from terrestrial interference, which improved the reliability of the results. Despite the careful methodology and advanced technology, the study faced significant challenges, mainly due to radio frequency interference. Innovative radio interference mitigation strategies, including signal injection and recovery testing, were crucial in differentiating terrestrial signals from potentially extraterrestrial ones. These efforts emphasize the difficulty of finding technological signatures, especially since the signals must be significantly more powerful than those detectable within our galaxy to be considered extragalactic. The exhaustive search resulted in 6,034,313 matches in all the galaxies observed. These matches represent cases in which the data analysis process has identified signals that potentially stand out from the background noise and that could be of interest for further studies. From the original 6,343,013 matches, further refinement and analysis using a computer algorithm reduced the field to 11,519 events of particular interest. The research team then meticulously examined these events to try to distinguish potential extraterrestrial signals from the ubiquitous RFI noise. Despite the complexity, the team ultimately concluded that all 11,519 events were associated with terrestrial sources or cosmic phenomena. However, the work done by Chosa and her team not only illuminates the path we have traveled, but invites us to reach new horizons. The ability to reanalyze the data through the subtle prism of machine learning promises the opportunity to discover signals that previously remained hidden or were perceived as noise. This changing landscape of SETI research, constantly enriched by technological innovation, invites us to delve deeper as we move forward, armed with improved tools and a deeper understanding of the challenges that lie ahead. Meanwhile, the search for extraterrestrial technological signals continues, and we eagerly await new opportunities to solve the mysteries of the cosmos. In the midst of the silent expanse of our solar system lies a world of profound mystery and rugged beauty. Mars, with its purple dunes and ancient valleys, speaks to us of its tempting past. A planet where sunsets tinge the sky blue, where towering dust devils roam the arid lands, and where the remains of water currents silently tell the story of times past. Here, among the red dust, lies the enigmatic brain terrain, a geological marvel that defies explanation. Its intricate patterns, reminiscent of the complex folds of the human brain, remain one of Mars' most challenging mysteries. What forces created these mysterious formations? Are they key to unlocking the secrets of Mars' climatic past? As the sun sinks into the horizon, the Martian sky transforms, projecting a blue light on the landscape. The scars of ancient rivers and the cracks of dry mud tell the story of an era in which water flowed freely on Mars, when the planet experienced the change of seasons, and when this world could have been more similar to Earth than we could have imagined. However, despite all its wonders, Mars clearly reminds us of its alien nature. Today we will travel to Mars, a world of beauty and mystery, a planet holding the keys to our past and the promise of our future. Join us as we explore the mysteries of the good old red planet. Under the purple skies of Mars lies a canvas of geological mysteries. Among them is the cerebral terrain, complex patterns resembling the cerebral cortex that extend through the Martian mid-latitudes. Its origin remains shrouded in mystery. What processes could have created such intricate patterns? Scientists suggest that sublimation, the direct conversion of ice into vapor, plays a key role here. Although the exact process remains a mystery, it is very likely that the relentless interaction between underground ice and the thin Martian atmosphere forms the intricate patterns. But Mars is not a still world. It breathes and moves. The dust devils, those imposing columns of dust that rise kilometers into the rarefied atmosphere, are not only a spectacle of nature, but also architects of the Martian surface. The arid landscapes they crisscross leave behind dark traces that bear witness to their passage. These ethereal giants, born from the interaction of heat and wind, reach more than 3 kilometers in height and are larger and more spectacular than their terrestrial counterparts. Then, as the Martian day fades, the sky transforms, and a Martian sunset bathes the landscape with an ethereal blue light that contrasts sharply with the familiar red and orange tones of the day. This phenomenon occurs due to the unique interaction of sunlight with the atmosphere of the red planet, full of iron dust particles, which when crossing the red part of the visible spectrum of sunlight is scattered by the dust particles, leaving only a fascinating blue glow. Although this scattered light tinges the sky red at sunset and transforms into blue tones at night, the mysteries of the Martian atmosphere do not end there. They end there. The interesting phenomenon of the green glow of Mars, recently captured by the NASA Odyssey orbiter, offers a vision of the unique characteristics of the Martian atmosphere. This glow, observed from orbit, results from atmospheric processes common throughout the solar system, but which manifest differently on each planet due to variations in the composition and density of the atmosphere. During the day, sunlight interacts with the Martian atmosphere, breaking down CO2 molecules through a process known as photodissociation. This releases individual atoms that, when colliding with the night side of the planet, recombine into different molecules while emitting light. On Earth, this phenomenon produces a whole spectrum of colors, but on Mars the predominant color is green. This green glow is mainly due to the recombination of CO2 molecules in the upper atmosphere, an altitude of between 25 and 90 miles. Interesting studies have revealed an additional glow at lower altitudes, resulting from the recombination of oxygen atoms. This secondary glow, visible during the Martian summer, is concentrated in the polar regions, where atmospheric currents converge. The intensity of this glow varies with the time of year, alternating between the northern and southern hemispheres. The thinness of the Martian atmosphere compared to the terrestrial one allows us to observe and study these luminous phenomena more directly, has allowed us to detect other emissions, such as those of nitrogen oxide in the ultraviolet spectrum, which further enriches our knowledge of the composition and behavior of the Martian atmosphere. These atmospheric studies not only shed light on the processes that shape the Martian environment, but also provide valuable information about the past and present climatic conditions of the planet. Speaking of it, the Martian landscape, with its vast deserts and its imposing volcanoes, contains a large amount of clues about the climatic past of the planet. Among them are the signs of seasonal changes that have shaped the surface for millennia. The presence of characteristics, such as the mud cracks discovered by the Curiosity rover, which bear a striking resemblance to similar objects on Earth, suggests the presence of liquid water in the planet's past. In particular, it is believed that the mud cracks were formed over many Martian seasons, indicating a cycle of wet and dry periods that Mars experienced in the past. Further evidence of Mars' dynamic climate can be found in the remains of ancient glaciers in the planet's mid-latitudes. These fossilized archives printed on the Martian terrain speak of an era when water ice slid across the surface of the planet, digging furrows and transporting sedimentary rocks. These glaciers, like their terrestrial counterparts, shaped the terrain, leaving behind traces of their presence in the form of seas and excavated valleys. This activity suggests that Mars has undergone significant climate changes, perhaps similar to the glacial and interglacial periods observed on Earth. The presence of sulfates in the mud cracks adds another layer to our understanding of the history of water on Mars. Mud cracks, such as those found on Earth, are formed by the drying of sedimentary rocks, indicating the presence of stagnant water that periodically evaporates, leaving behind these prominent patterns or sinking below the surface. The detection of sulfates in these formations indicates that the water interacted with the Martian soil, resulting in the deposition of minerals. The different levels of these sulfates, combined with the pattern of the mud cracks, paint a picture of a planet where water levels rose and fell, creating conditions conducive to chemical reactions that could even sustain the precursors of life. Clearly, the search for water on Mars is a key aspect to understanding the geological history and the potential for habitable life on the planet. Recent discoveries have shed light on the presence of water in various forms and places on Mars, significantly changing our understanding of the red planet. On Mars, there are a large number of geological features that indicate the presence of water in the past. The discovery of ancient lake beds, river valleys, and drainage channels indicates that at some point water flowed freely across the surface of the planet. These features suggest that Mars once had a warmer and more humid climate, capable of harboring liquid water on its surface. The presence of sedimentary layers and mineral deposits in these ancient lakes and fluvial valleys further reinforces the idea of prolonged hydric activity lasting thousands or even millions of years. One of the most revolutionary discoveries is the finding of water ice near Mars' equator. Traditionally, ice was thought to be found only in the polar regions of Mars, where it is visible on the surface. However, radar studies and analyses have revealed ice deposits under the surface in lower latitudes, even near the equator. This refutes previous ideas about the climate of Mars and suggests that water ice is more widespread throughout the planet than previously thought. The implications of the equatorial ice extend to the climatic history of Mars and its potential habitability. The equatorial ice deposits indicate a more complex hydrological cycle on Mars than previously believed. This could mean that, in the past, Mars had a climate more similar to that of the Earth, with water circulating between the atmosphere and the surface. However, This presence does not at all raise the possibility that adequate conditions for life existed on Mars in the past, much less in the present. Water is key to life, but such a contrasting climate change cannot offer many possibilities for a long development process of any life form. The search for biosignatures, such as special minerals, organic molecules, or erosion patterns that may indicate past biological activity, continues, though no conclusive evidence of life on Mars has yet been found. The presence of water in various forms continues to maintain a minimal possibility. Even so, these ice deposits could serve as a valuable resource for the future human exploration and colonization of the planet, providing water for drinking, agriculture, and fuel production. If we look more closely at the Martian landscape, we see a marked contrast with the rich diversity found on Earth. On our planet, about 6,000 different minerals have been discovered, which testifies to the dynamic geological processes of the Earth and the complex interaction between the biosphere and the geosphere. These minerals have not only been formed by abiotic processes, but have also been significantly influenced by the presence of life, which has contributed to mineral diversity through various biochemical interactions. In comparison, after 5 decades of research, only have been on the Martian surface. This divergence in mineral diversity is not only a numerical difference, but tells us a lot about the differences in geological activity and the two planets' histories. The scarcity of minerals on Mars has profound implications for our understanding and the potential of the planet, its potential to harbor life. The diversity of minerals in a planetary body is usually a reflection of its geological and environmental dynamism. On Earth, plate tectonics, the availability of water, and atmospheric processes contribute to the wide range of physical and chemical conditions essential for the origin and maintenance of life. Complex organic molecules, including DNA precursors, often require diverse chemical environments and carbon catalysts. Therefore, the limited mineral diversity of Mars raises some questions about the habitability of the planet as a whole. The scarcity of diverse minerals on Mars also indicates that the planet may have had a more monotonous geological history compared to Earth. However, is it as calm and peaceful as it seems? Recent studies of Mars' internal structure have led to interesting discoveries, particularly through the analysis of seismic data. The InSight mission played a key role in this discovery before its completion by detecting what is believed to be the largest earthquake ever recorded on Mars. This earthquake, which lasted about 6 hours, did not fit the typical profile of a meteorite impact, as it left no crater, suggesting that it originated in the planet's depths. The magnitude of the earthquake, which was 4.7 on the Richter scale, points to significant geological activity below the surface. Unlike Earth, Mars lacks tectonic plates, which raises questions about the mechanisms that cause these earthquakes. The absence of tectonic plates suggests that Martian earthquakes may be related to internal stresses or other geological processes that. Volcanic activity on Mars, both recent and ancient, has left indelible marks on its surface. Recent studies have found at least 40 different volcanic events, some of which occurred only a few million years ago. In addition, the discovery of unusual polygonal structures under the surface, found by the ground-penetrating radar of the Chinese rover Churon, indicates a history of thermal contraction and expansion and speaks of these structures, whose size varies between a few centimeters and several meters, have been found at a depth of about 30 meters. It is evident that a drastic climate change or some cataclysmic event has caused these deposits to be so deep below the surface of the planet region known as Noctis Labyrinthus, with its vast network of valleys and canyons, is further evidence of Mars' volcanic past. Located near the Tharsis Volcanic Plateau, which houses the largest volcano in the solar system, Olympus Mons, this region demonstrates volcanism's dramatic impact on the Martian landscape. A video simulation provided by ESA shows how the Olympus Mons. This region demonstrates the dramatic impact of volcanism on the Martian landscape. A video simulation provided by the ESA shows how the stretching and flexing of the Martian crust in this region, which led to the formation of deep valleys and canyons, is evidence of the planet's active geological past. The release of water during volcanic eruptions may explain the presence of ancient river valleys and lakes, allowing us to glimpse an era when Mars may have been more like Earth, with a warmer and more humid climate. Understanding the planet's volcanic history not only sheds light on its past climate and its potential to harbor life, but also helps in future research, as regions with past volcanic activity may contain clues about the planet's habitability and the availability of vital resources. Speaking of habitability, it is impossible not to mention the recent successes in the production of oxygen on Mars. The Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, was an achievement of space technology that managed to produce oxygen from the carbon dioxide in the Martian atmosphere. Installed aboard NASA's Perseverance rover, MOXIE operates efficiently in various Martian conditions, both day and night, and in different climatic states of its ability to convert CO2 into oxygen through the solid oxide electrolysis process is a significant technological achievement. By heating the Martian atmosphere to 800 degrees Celsius, MOXIE decomposes CO2 into oxygen ions and carbon monoxide, and then recombines the oxygen ions into breathable O2. This process has been shown to achieve the required oxygen production and purity, despite design trade-offs due to mass, power, volume, and cost constraints associated with space missions. MOXIE's success has profound implications for the future of human exploration and potential colonization on Mars. The ability to produce oxygen on Mars paves the way for a sustainable human presence, reducing dependence on Earth for critical resources. The studies indicate that a large-scale version of MOXIE could generate tens of tons of oxygen, essential not only for the life support of astronauts, but also as a critical component in rocket fuel. Such capacity would significantly reduce the logistical and financial burden of transporting oxygen from Earth to Mars, which would otherwise require launching hundreds of tons of material into space at an exorbitant cost. By providing a reliable supply of oxygen, systems like MOXIE could support longer missions, larger crews, and even permanent settlements on Mars. In addition, the technology can be adapted to produce other necessary resources, such as water and fuel, a significant step towards realizing the dream of a self-sufficient human presence on the Red Planet. Speaking of the Perseverance rover, we must also mention its Ingenuity helicopter, which has far exceeded the original parameters for its mission on the Martian surface. Built solely for a brief technological demonstration, it was supposed to perform only 3 flights in 30 days, but it far exceeded those expectations by performing 72 missions over more than 1,000 Martian days, demonstrating its resilience and adaptability to the harsh Martian environment. This achievement not only marked an important milestone in the aerial exploration of other planets, but also laid the groundwork for future missions. Ingenuity's journey was not without difficulties, as it encountered numerous technical problems, such as communication outages and unexpected landings. Despite these challenges, Ingenuity continued to push the limits of what is possible and even set a new distance record on one of its flights. The vehicle's ability to survive and function despite Martian dust storms, extreme temperatures, and even sensor failure demonstrates the reliability of its design and the careful planning by the team. However, the mission ended unexpectedly when a significant portion of the blade of one of Ingenuity's rotors was damaged, making it impossible to continue flying. This incident marked the official end of the Ingenuity Mars mission. It took place in January 2024. However, the conclusion of Ingenuity's missions does not detract from its extraordinary achievements or the valuable data it has provided. NASA has already begun to apply the lessons learned from operating aircraft in extraterrestrial environments to upcoming missions, including the Dragonfly mission to Titan, Saturn's largest moon. Ingenuity's success has opened the door to a more ambitious use of aircraft for tasks such as sample recovery, which could significantly increase the efficiency and scope when exploring other planets. During its long stay on the Red Planet, the Perseverance rover has accumulated a considerable number of samples of Martian rock materials. However, It should be noted that the effort to return samples from Mars to Earth is both the pinnacle of scientific endeavor and the height of logistical challenges. The financial implications are staggering. According to recent estimates, the costs could exceed those of the most expensive space missions, such as the James Webb Space Telescope, totaling $11 billion. The complexity of extracting samples from the Martian surface and transporting them back to Earth involves multiple spacecraft and precise robotic operations. This task requires not only precision engineering and unprecedented navigation solutions, but also significant financial outlays, raising questions about budget allocation and priorities for space exploration. When it comes to prioritizing space exploration, humanity faces another unresolved challenge: the ongoing debate about cooperation, precision engineering, and unprecedented navigation solutions, but also significant financial outlays, raising questions about budget allocation and priorities for space exploration. When it comes to prioritizing space exploration, humanity faces another unresolved challenge. The ongoing debate about international cooperation in the exploration of Mars is multifaceted and involves political, scientific, and logistical considerations. On the one hand, cooperation can pool resources, share risks, and increase the scientific yield of missions through the diversity of specialized knowledge. On the other hand, comparing the successes of collaborative efforts, such as the International Space Station, against the backdrop of some international limitations, highlights the contradiction between the ideal of a united human effort in space exploration and the reality of international relations on Earth. Another test, but not the last, on our path is that, as Mars becomes a center of exploration and possible colonization, the problem of space debris is becoming increasingly important. The accumulation of debris in Martian orbit can pose a danger to spacecraft, impede navigation, and endanger missions. This problem is not only theoretical. The proliferation of debris around Earth has already created an urgent need for sophisticated tracking and avoidance maneuvers that, in turn, solving this problem on Mars will require proactive measures to prevent the accumulation of debris and, possibly, the development of debris reduction and removal technologies to ensure the safety and sustainability of future missions. The colonization of Mars, which was once the stuff of science fiction, is increasingly entering the realm of the possible thanks to technological advances and scientific discoveries. The successful demonstration of in situ resource utilization through experiments such as MOXIE, the potential to use local materials for construction, and advances in life support systems are gradually laying the foundation for a sustainable human presence on Mars. However, the vision of colonization goes beyond technological challenges and includes ethical, social, and environmental considerations. The responsibility of extending humanity's footprint to another planet raises questions about how we treat Earth and to what extent we will be able to apply these lessons to the new world. The future of Mars exploration is promising and full of challenges. As we stand on the threshold of these efforts, the collective wisdom, ingenuity, and spirit of cooperation of the global community will play an important role in overcoming these challenges and realizing the dream of expanding humanity's presence beyond Earth. Let's imagine a canvas of moments woven with the threads of time and matter that extends infinitely in all directions, capturing every choice, every event, every heartbeat. What if we could navigate this intricate fabric? What if we could go back in time, look to the future, or even change the course of history? Time governs our lives, but remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debates. But what does science say? Can time travel ever move from the pages of science fiction to the annals of science? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light, but time itself. Did you know that astronauts aboard the International Space Station age more slowly than humans on Earth, even if only for a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let's travel through the corridors of time and explore the scientific paradoxes and limitless possibilities that could one day make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humanity was fascinated by the skies and the passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating elaborate calendars and methods to measure time. Transported to the modern era, this fascination finds a new canvas in literature and cinema. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that one could navigate through time as through the dimensions of space. Then came Back to the Future, a pop culture phenomenon that took the concept of time travel and made it accessible to a new generation. Who could forget the DeLorean, the flux capacitor, the magnetic condenser, and Doc Brown's charming eccentricity? His charming eccentricity? But this is not just a Western phenomenon. The charm of time travel knows no cultural or linguistic boundaries. From Steins Gate in Japan to the Soviet film Ivan Vasilovich Changes Profession. The theme of time travel resonates across the world. So, what attracts storytellers to this concept? The charm of rewriting history, the emotion of the unknown, or perhaps the philosophical questions that these journeys raise? A desire fueled by a mixture of nostalgia and expectation, a longing to relive fond memories or to launch into the promises of tomorrow. And now that we find ourselves on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we, should we, and what would happen if we traveled through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like MC2 are not just symbols, keys to understanding the universe, but could they unlock the secrets of time travel? From the big screen to the televisions in our living rooms, time travel has been depicted in countless ways. But let's set fiction aside and delve into the science that can make time travel more than just a plot device. Let's get to know space-time, the four-dimensional fabric of our universe, according to Einstein's theory of relativity. Einstein's theory of relativity. This fabric can be bent and deformed by mass and energy, but can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of movement or the gravitational field. For example, astronauts on the International Space Station age slightly more slowly than people on Earth. Experiments with gas particles and atomic clocks have provided empirical evidence for time dilation. Particles traveling at speeds close to that of light have been observed to decay more slowly than their stationary counterparts. Wormholes are hypothetical tunnels in space-time that, in theory, could shorten time and space. Although they are somewhat speculative, mathematics suggests that they are indeed possible. Leading physicists and cosmologists have expressed their views on the matter, offering theories ranging from the plausible to the bizarre. Some even suggest that quantum mechanics, the science of the very small, could play a role in making time travel possible. And let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space, but also time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from reaching any consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of time itself. They say that time always moves forward, never backward. But what if we could take a leap forward, skipping years, decades, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the key parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already been achieved, albeit on a minuscule scale. astronauts aboard the International Space Station experience time dilation and age slightly more slowly than their counterparts on Earth. Let's now focus on the twin paradox, the famous thought experiment that takes time dilation to another level. Let's imagine two twins separated at birth. One travels through space at nearly the speed of light, while the other remains on Earth. Upon reuniting, the space twin will appear younger. Reaching speeds close to that of light would greatly enhance this effect, but such speeds are currently beyond our technological reach, not to mention that the energy requirements would be astronomical. Scientists and engineers are grappling with these problems, investigating propulsion technologies that could one day make it possible to travel at speeds near that of light. But even then, could the human body withstand such a journey? Let's imagine a future where time dilation capsules are as common as airplanes, allowing people to jump to the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of future be a gift or a curse? And what will it mean for free will? From science fiction to scientific articles, wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time could turn out to be the cosmic shortcuts we've been dreaming of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch, then piercing it with a pencil in space-time. The wormhole would be that pencil, creating a direct path between two distant points. This concept gained popularity in the scientific community thanks, in part, to Carl Sagan. While writing his novel Contact, he consulted physicist Kip Thorne to explore the scientific possibility of using a wormhole for travel between stars. Today, physicists are delving into the mathematics of wormholes. While the general theory of relativity allows their existence, the equations also assume they collapse too quickly for anything to pass through. In theory, by introducing some exotic matter, for example, the gravitational forces that cause the wormhole to collapse could be counteracted, keeping it open long enough for something or someone to pass through it. The representation of wormholes in popular media often overlooks these complexities. They are usually depicted as stable luminous vortices, but the reality, if they exist, may be far more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a vibrant area of research. Scientists use computer models and indirect observations to understand their properties and potential uses. Let's imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present and the other in the future or past. The implications for research and even for preventing global catastrophes are astonishing. Wormholes open the door to questions not only about where we could go, but also when. As we approach the possible discovery of these cosmic shortcuts, we must ask ourselves if we're prepared for the responsibility that comes with such power in the world of the very small, where particles are also waves and reality itself seems diffuse. In the quantum world, this region of uncertainty could hold the keys to unlocking time travel. Quantum mechanics challenges our everyday understanding of world. Let's take the double-slit experiment, in which particles behave like waves. This duality suggests that, at the quantum level, the fabric of reality is far more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that has been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics may offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers like ghosts through walls. In the double-slit experiment, can a similar principle allow time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable for classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for today's computers. The concept of quantum entanglement adds interest. Imagine two particles linked in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly amazing aspect of entanglement is that the state of one particle instantaneously affects its entangled partner, regardless of the distance separating them, whether across the room or even across the galaxy. If the spin of one changes, the spin of the other changes instantaneously. Albert Einstein called it spooky action at a distance. At first, he did not like this idea because it seemed to violate the speed of light limit established by his theory of relativity. However, since then, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Did he like this idea because it seemed to violate the speed of light limit established by his theory of relativity? However, since then, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could a remote effect like this make a difference in instantaneous time travel? Although the section of quantum mechanics and time travel is still in the realm of speculation, it is a hot topic in scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Let's imagine a future in which the principles of quantum superposition could explain multiple timelines or realities. What if we could exist in a superposition of the past and present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Let's move on from the world of the microscopic scale to the grandly large. Black holes, mysterious titans of space whose gravity is so strong that not even light can escape. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves, CTC. A closed time-like curve, or CTC, is a trajectory in space-time that repeats itself. Theoretically, an object or even a person traveling along a CTC could end up at an earlier time. The idea was first proposed in 1949 by physicist Kurt Gödel. Gödel's solution to Einstein's field equations suggested rotating universes could contain looping trajectories. However, these solutions required specific conditions, such as a universe full of rotating matter. Although the Gödel model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which CTCs can exist without violating the laws of physics. One such scenario involves rotating black holes known as Kerr black holes. The enormous gravitational and rotational forces can, in theory, twist spacetime into loops creating CTCs, but there is a drawback. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped instead of point-shaped. This ring feature could potentially serve as a gateway to a CTC. However, the powerful gravitational forces could also create a barrier known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with uncertainties and paradoxes. For example, if CTCs exist, they could lead to paradoxes where cause and effect are reversed. This has led some physicists to propose the chronology protection conjecture, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Could we ever safely navigate such a treacherous region of space-time? And if we could, what would we find on the other side? Another universe or another time? In addition to black holes and closed curves in time, another cosmic mystery could open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe could be remnants of the Big Bang. Cosmic strings are believed to have formed in the early universe as it cooled after the hot, dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense and would have had tremendous gravitational force. Although still theoretical, cosmic strings offer intriguing possibilities regarding time travel. The physicists Richard Gott and William Hiskett have made important contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could, in theory, distort space-time enough to create a loop that would allow travel to the past or the future. However, the existence of cosmic strings remains a matter for debate. Their detection would require astronomical observations on scales that currently exceed our capabilities. Furthermore, if they existed, harnessing their power for time travel would be quite a challenge. Let's go back now to quantum entanglement. We have already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be united in time? Some theories suggest entangled particles can be used to transmit information not only in space, but also in time. Let's imagine a future where quantum entanglement is used to create a quantum internet that allows instantaneous communication between eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics full of unanswered questions and untapped potential. Research is exploring how both phenomena could be connected and what this could mean for our understanding of time travel. Imagine a scenario where cosmic strings are manipulated at the quantum level through entanglement. This would represent a fusion of the very large and the very small, a meeting point between the cosmic and quantum scales that could revolutionize our concept of time travel. As we delve into the realm of time travel, we face many enigmas and paradoxes. These are not just intellectual exercises, but fundamental questions that can either make or break the possibility of time travel. First, there is the grandfather paradox. Imagine you go back in time and prevent your grandparents from meeting. If they never meet, one of your parents will never be born, and therefore neither will you. But if you were never born, how could you travel back in time? The grandfather paradox raises questions about causality and the very nature of time. Some theorists suggest these paradoxes can be resolved by the existence of parallel universes, where each resolution generates a new timeline. Another confusing paradox is the so-called bootstrap paradox, which gets its name from the popular expression, pulling oneself up by one's bootstraps. Imagine you go back in time to give Shakespeare a copy of your plays, which he then claims as his own. In that case, where did those works originate? The bootstrap paradox creates a closed loop of cause and effect without an apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox involves the paradox of predestination. It occurs when the actions of a time traveler in the past lead to the event that he was trying to avoid. This raises questions about free will and determinism, and whether we can truly alter the course of history. The study of time travel paradoxes is not just a game for philosophers. It is an area of serious research in physics and metaphysics. Resolving these paradoxes could shed light on time travel itself. As we stand on the threshold of scientific discovery, the future of time travel remains a mystery, shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching real science. From cosmic strings to quantum entanglement, from rotating black holes to closed time-like curves. We have explored the theories and possibilities that could one day make time travel a reality. Current investigations are paving the way for new experiments, new technologies, and perhaps a new understanding of reality structure. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we prepared for what we might find? Time waits for no one. But what if we could wait for time itself? Humanity stands on the threshold of a new era, defined not only by exploration, but by the bold dream of colonization. For decades, our gaze has been fixed on the familiar. The moon, our celestial neighbor, and Mars, the red beacon in our night sky. These worlds, once the subject of science fiction, now beckon us with the promise of new frontiers. But beyond these well-traveled paths lies a world shrouded in mystery, a world that is changing our understanding of what it means to be a moon. This is Titan, Saturn's largest satellite. Titan is a world covered by a dense atmosphere, which is unusual for a moon. It is a place where rivers and lakes flow, not of water, but of liquid methane and ethane. Here, it rains gasoline, and the cold is more intense than anything experienced on Earth. However, within this alien landscape lies the potential for something extraordinary. Could Titan a world so different from our own, be key to our future in space? Could this distant moon hold the secrets not only to survive, but to thrive beyond our home planet? A small step for man, one for humanity. As we turn the pages of our history of space exploration, the moon and Mars become beacons of human ambition. The moon, our closest celestial neighbor, has always been a constant companion in our night sky, symbolizing our desire to leave the confines of our planet. Mars, in turn, with its Earth-like qualities, fuels our dreams of finding a new home in space. However, the moon, despite its proximity, presents significant problems. Its surface is a barren wasteland, without an atmosphere and offering no protection against the harshness of space. The lunar environment is a vacuum that exposes astronauts to extreme temperatures and cosmic radiation. The absence of an atmosphere means there is no air to breathe, no wind to carry sound, and no sky to protect us from the relentless bombardment of solar and cosmic rays. Mars, although more Earth-like, is not without its problems. Its atmosphere, composed mainly of carbon dioxide, offers little protection against solar and cosmic radiation. The Martian environment is harsh and unforgiving, and temperatures at the poles can drop to minus 27 degrees Celsius. The lack of a global magnetic field exposes the surface to the full force of the solar wind and cosmic rays. In contrast, Titan, Saturn's largest satellite, presents a very different environment, enveloped by a dense atmosphere. Titan offers a natural barrier against the dangers of cosmic radiation. This atmosphere, richer in nitrogen than that of the Earth, is the key to protecting future settlers from the cosmic rays that relentlessly bombard less protected worlds such as the Moon and Mars. Titan's atmosphere is not just a shield. It is a gateway to opportunities. Unlike the Moon and Mars, the atmospheric pressure on Titan's surface is 15 times greater than on Earth, creating a pressure environment surprisingly familiar to human explorers. This dense atmosphere opens new possibilities for exploration and colonization, possibilities beyond the reach of our more trivial space goals. As we rethink our goals for space colonization, Titan becomes an attractive alternative, a world where the atmospheric and radiation problems that limit our ambitions on the Moon and Mars become its strengths. Titan invites us to imagine a future in which humanity can thrive under the protective embrace of an alien sky. A future in which the mysteries of this distant moon become stepping stones for our expansion into space. As we mentioned earlier, Titan, a moon full of mysteries, orbits Saturn and was discovered in 1655 by Dutch astronomer Christian Huygens. Since then, Titan has captivated the imaginations of scientists and dreamers. This world is both similar to and very different from our Earth. Titan's environment is unlike anything else found in our solar system. It is the only known moon with a dense atmosphere and the second largest moon in our solar system after Ganymede, a satellite of Jupiter. But it is not only its size that makes Titan stand out, but the rich composition of its atmosphere and surface that really sets it apart. This moon is surrounded by a thick atmosphere rich in nitrogen, similar in composition to Earth's, but much denser and more extensive. It is impregnated with organic molecules that create a kind of diffuse orange glow that hides the surface of the satellite from view. This nitrogen-rich atmosphere protects against solar radiation, a sharp contrast to the arid skies of the Moon and Mars. Under this alien sky lies a landscape both familiar and utterly strange. The surfaces of Titan are made up of rivers and lakes, but they are not bodies of water as we know them, but are filled with liquid methane and ethane that flow through channels carved into the icy crust of the moon. These hydrocarbon seas are a true marvel, a testament to the universe's diversity. Titan's chemistry. The presence of these fluids on the surface is a key feature that distinguishes Titan from other celestial bodies on Earth. The water cycle shapes Titan's climate and geography. A similar cycle occurs on Titan, but methane and ethane play the role of water. This hydrocarbon cycle, with methane rains and ethane lakes, creates a dynamic environment that can provide clues to understanding the complexity of planetary atmospheres. Thus, by pushing the limits of our perception, we gradually discover what makes a planet or moon habitable. Its nitrogenous atmosphere and surface fluids open the door to new possibilities. Let's discover what they might be. The moon's nitrogen-rich atmosphere provides a natural barrier against cosmic radiation, a main challenge for space colonization. Why do we pay so much attention to solar radiation? The answer is simple, yet profoundly important. Solar radiation relentlessly destroys living cells. It affects not only microscopic life forms, but also directly affects us humans. Unprotected exposure to solar radiation can cause serious cellular damage, destroying the very structure of our biological existence in space. By spreading uncontrollably, this radiation poses one of the greatest threats to the survival and health of astronauts on Earth. On Titan, it is the atmosphere and magnetic field that protect us. It is the dense nitrogen atmosphere that provides vital protection, making it a safer haven for future human colonists than the arid landscapes of the Moon or Mars. Under this protective dome lies a world of liquid methane and ethane. These hydrocarbon lakes and rivers contrast radically with bodies of water we know on Earth and offer intriguing possibilities. Imagine a world where ships sail on seas of methane, where the familiar concept of the water cycle takes on a completely new form. The presence of these surface fluids is not just a curiosity, it's a resource. Methane and ethane could be used as fuel, providing energy for future colonies. This abundance of hydrocarbons makes Titan an attractive target for colonization, offering a solution to a major problem of space habitability, sustainable energy. But Titan's gifts do not end here. Beneath its icy surface lies another treasure, water ice. Water, so essential to human life, is abundant on this satellite, trapped in its icy crust. The presence of water ice and hydrocarbons makes this moon a repository of vital resources, laying the foundation for a self-sufficient human presence far from Earth. Titan, a world of incalculable potential, also presents enormous challenges. The extreme cold, with temperatures dropping to minus 356 degrees Fahrenheit, creates an environment unsuitable for human life as we know it. In addition, methane rain, a phenomenon unique to this moon, adds another layer of complexity to survival. To overcome these challenges, we must draw on the pinnacle of human ingenuity and technology. Colonizing Titan will require not only adaptation, but a complete rethinking of human habitability in extreme conditions. Imagine homes designed to withstand low temperatures, insulated with materials yet to be invented, and harnessing energy from Titan's own resources to provide warmth. These habitats could be equipped with systems to convert atmospheric methane into heat, turning the problem itself into a solution. But survival is more than just staying warm. Methane rain, although an obstacle, could become an advantage. Advanced collection and filtration systems could recycle methane not only as an energy source, but also as a raw material for essential products. Now, let's imagine a human colony on Titan. Imagine domed cities, with architecture combining science and art, designed to harmonize with Titan's unique environment. These structures, resistant to cold and methane rains, would be interconnected, forming a network that would demonstrate human resilience in the face of alien conditions. Within these domes, life would thrive. Hydroponic gardens would provide food, recycling systems would conserve resources, and public areas would foster a sense of community. It is a place where humanity not only survives, but flourishes, decisively adapting to Titan's challenges. Colonizing Titan is not just a distant dream. It is a future that invites us to accept the challenge. With each technological advance, with each bold leap of imagination, we get closer to making this alien world a new home for humanity. Upon observing the prosperous human colony on Titan, it is clear that this moon is more than just a new home for humanity, a center of economic and scientific opportunity. Its unique environment and abundant resources offer unprecedented perspectives. The economic benefits of colonizing Titan stem from its vast hydrocarbon reserves. The key components of Titan's lakes and atmosphere are not only potential sources of energy, but also valuable raw materials for chemical synthesis. The capacity to take advantage of these resources could turn Titan into an economic hub that satisfies the needs of the colony and, potentially, supplies materials for interplanetary commerce. From a scientific point of view, Titan is a gold mine. Its complex atmosphere and surface chemistry offer unique research opportunities that allow delving into organic chemistry and astrobiology. The study of Titan's methane cycle and its prebiotic chemistry could reveal the secrets of the origin of life, not only on Earth, but potentially throughout the cosmos. In addition, Titan's position in the solar system and its resources make it an ideal launch platform for future space explorations. Its low gravity and abundant fuel reserves could facilitate the launch of spaceships to distant destinations, which would turn Titan into a strategic advance post to explore the outer solar system and beyond. However, these opportunities bring with them important ethical considerations. When embarking on the colonization of Titan, we must reflect on our responsibilities when interacting with this new world. The conservation of the environment of Titan, the respect for its unique characteristics, and a careful management are fundamental. We must approach Titan not as conquerors, but as custodians. The way in which we relate to this world will reflect our values and our capacity to balance progress and responsibility. When concluding our trip, let us reflect on the key points. A moon that was previously wrapped in mystery has turned out to be a world full of potential. We have explored the protective properties of Titan's nitrogen-rich atmosphere, a natural shield against the dangers of cosmic radiation. We have traveled through alien landscapes where rivers and lakes of methane and ethane cross icy terrains, offering resources that could secure our future in space. Our trip has also taken us to the potential of a vibrant human habitat where ingenuity and resilience have turned challenges into opportunities. We saw how the economy of Titan, driven by its abundant resources, can be the cornerstone of our interplanetary efforts. As we reflect on the future of humanity on Titan, we remember that colonization is not only about reaching technological perfection. It is a trip that forces us to grow, learn, and respect the universe in which we live. So we leave you with a great question. What does this step mean for humanity's future? How will our efforts on this distant moon affect our destiny in the vast, unexplored expanse of space? In the vast theater of our solar system, where planets like Jupiter and Saturn usually attract attention with their majestic rings and violent storms, there is a distant world wrapped in mystery and intrigue: Uranus. An enigmatic ice giant that often goes unnoticed, but hides secrets that could reveal some of the most enduring mysteries of the cosmos, much further beyond the asteroid belt, nestled between the orbits of Saturn and Neptune. Your trip through the cold and dark corners of our solar system is to a world that lives at a different rhythm, rotating on its side, a rarity that has long puzzled astronomers and has given rise to countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered via a telescope, expanding the known limits of our solar system. For centuries, this distant world was nothing more than a point of light in our telescopes, a ghostly blue ball, distant and remote, that kept its secrets. But now, with the arrival of the James Webb Space Telescope, a new chapter opens in Uranus exploration. The JWST, with its unprecedented vision, discovers the layers of this ice giant, revealing a world of incredible beauty and complexity. Let us travel together to this mysterious ice giant and discover the latest findings made by the James Webb Space Telescope. In its search to understand the universe, humanity has launched a sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, successor to the legendary Hubble Space Telescope, equipped with a set of advanced instruments and a mirror of more than 62 m in diameter. The JWST is designed to observe the universe in light invisible to the human eye, the infrared spectrum. This allows the telescope to see through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey to space was a feat in itself. Launched on an Ariane 5 rocket, the JWST traveled to a point in space known as second journey to space was a feat in itself. Launched on an Ariane 5 rocket, the JWST traveled to a point in space known as the second Lagrange point, or L2, a million kilometers from Earth. Here, in this stable orbit, the JWST can observe the universe with minimal interference from the Earth and Sun. The JW's capabilities are not limited to observing the primitive universe or distant galaxies, but it plays a key role in revealing the mysteries of our solar system. Its powerful instruments, such as the NIRCam near-infrared camera and the MIRI mid-infrared instrument, reveal new details about planets, moons, and other celestial bodies closer to us. Let us take Uranus as an example. In the past, our vision of this distant planet was limited to blurred images obtained with telescopes like Hubble. But now, thanks to the improved infrared capabilities of the JWST, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe its climatic patterns and even its mysterious rings with unprecedented clarity. By analyzing Uranus light, the JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also gives us clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations and reveal more details about our universe every day. Its latest triumph is a series of very recent images of Uranus, surpassing even the impressive observations made in April 2023. At the beginning of 2023, the JWST provided us with unprecedented views of Uranus, which allowed us to observe the atmospheric dynamics and the planet's ring system in a new light. However, the new images go one step further. Not only are they sharper, but they reveal aspects of Uranus that were previously hidden or blurred, even in the April observations. Let us take the rings of Uranus as an example. The latest images show them with greater clarity, which allows us to observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta Ring, an incredibly thin ring located closer to the planet. The strength of the JWST does not only reside in its punctual observations, but also in its capacity to continuously track celestial objects. The continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, follow the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are especially striking. The bright white layers and dark bands near the poles, whose origin is still unclear, have shown notable changes. This continuous observation provides valuable data to understand the seasonal changes and long-term climatic patterns of Uranus. In the set of planets of our solar system, Uranus stands out for a peculiar characteristic, an extraordinary axial tilt, different from that of any other planet. Uranus rotates practically on its side, with a tilt of approximately 908 degrees. This unique orientation has long intrigued astronomers and triggered a search to understand its origin and consequences. To understand the meaning of this tilt, we must travel back in time to the early days of our solar system. Probably, Uranus formed with a much less pronounced tilt. The predominant theory suggests that a catastrophic event, perhaps a collision with an object the size of a planet, drastically changed its orientation. This colossal impact would have knocked Uranus to one side, changing its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and submerged in darkness at intervals of 42 years. This extreme tilt gives rise to extreme seasons, unlike those observed on other planets. The implications for observation and planetary research are enormous. The tilt of Uranus allows us to observe its rings and satellites from different perspectives, which offers information about their composition and dynamics. For example, when the rings of Uranus are oriented toward Earth, they become almost invisible, revealing fainter bands of dust and smaller satellites. Compare this with Earth, which is only tilted 235 degrees. The extreme tilt of Uranus causes drastic changes in its climatic patterns, a gold mine for scientists who study planetary climate. The tilt also affects the circulation of the atmosphere of Uranus. The prolonged exposure to sunlight of the poles can give rise to complex meteorological systems, as seen in recent images from a JWST. These systems are very different from those of other planets and constitute a unique laboratory to understand atmospheric physics. Let's travel through a Uranian year. Each season on Uranus lasts about 21 Earth years, as a consequence of its 84-year orbit around the Sun. This prolonged duration means that each hemisphere experiences long periods of daylight followed by equally long nights. As a result, the planet undergoes drastic changes in its appearance and climate, since one pole of Uranus bathes in uninterrupted sunlight during the summers, while the opposite pole is submerged in a deep, dark winter. This marked contrast creates unique atmospheric conditions that cause complex meteorological patterns and climatic changes. The impact of these seasonal changes on the atmosphere of Uranus is profound. When the sun illuminates the planet's surface, it heats the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static but evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking characteristics are the bright peaks of the clouds that appear when the sun illuminates them. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. On the contrary, dark spots of storms that look like giant hurricanes travel the surface of the planet. In addition, the seasonal phenomena of the planet not only affect the planet itself, but also its moons. A recent study of the moons of Uranus, or rather of a particularly intriguing phenomenon, is the development of temporary atmospheres in these moons, a spectacle caused by the unique conditions of the Uranian system. The key to understanding these temporary atmospheres lies in the extreme tilt of Uranus and its effect on the orbits of the satellites. As these satellites orbit the planet, they experience drastic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During the long summer, exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, is transformed directly from solid to gas, without passing through the liquid phase. This sublimation creates thin, temporary exospheres that envelop the satellites. These exospheres are more pronounced when the moons are warmer. Recent investigations by the James Webb Space Telescope show that this phenomenon is more dynamic and complex than previously thought. The exospheres are heterogeneous, varying in composition and density depending on the topography of the moons and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. The gases recondense on the surface and return to an icy state. This cycle of creation and disappearance of the atmosphere is a unique characteristic of the satellites of Uranus, which opens a window to the interaction between solar radiation and the surface ice. The rings of Uranus, often eclipsed by the majestic rings of Saturn, hold their own history of intrigue and cosmic dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but no less fascinating, celestial characteristics. Unlike the wide and bright rings of Saturn, the rings of Uranus are narrow, faint, and less extensive, extending up to 4 planetary radii. This includes rings difficult to observe, such as the Mu and Nu rings. The study delves into the gravitational influence of the main satellites of Uranus on these rings, a key factor in their formation and evolution. The significant influence of the 5 main satellites of Uranus, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and masses relative to Uranus provide a better understanding of the satellite's formation and the gravitational formation of the rings. The formation of the rings of Uranus is attributed to a combination of processes that include collisions, the rupture of satellites, and the release of gas from the main satellites. These dynamic processes affect the ring's material composition and are influenced by the constantly changing environment of the Uranian system. The stability of the rings is intrinsically linked to their dynamic interactions with Uranus satellites. The study examines how accretion processes occur within the Roche limit and how the dynamics of the shepherd moons play a crucial role in maintaining the rings. In addition, the rings offer a unique opportunity to understand Uranus' internal structure through seismological studies. The model's results show how these satellites shape the ring system, affecting its structure and stability over time. The model predicts significant material loss within the ring system, mainly due to gravitational interaction with the satellites. The complex interaction between the moons and rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the distribution of the material of the rings are crucial to understand the structure and the evolution of the rings. The study also examines the role of the interactions between satellites in the evolution of the system, especially the past resonances between satellites like Ariel and Umbella and their impact on the orbits and the geology of the satellites, especially Miranda. But the mysteries surrounding this planet do not end there. You have probably heard of the aurora borealis, while the latest discovery refers to Uranus auroras, which it also has. However, unlike Earth's, these auroras occur in the infrared spectrum. Using the KK-2 telescope, astronomers observed intensified trihydrogen cation emissions in the planet's atmosphere. This is a revolutionary discovery that sheds light on Uranus' magnetic field and the unique dynamics of its atmosphere. The magnetic field of Uranus, which deviates significantly from the axis of rotation of the planet, creates a unique coupling between the magnetosphere, the ionosphere, and the thermosphere. The detection of these infrared auroras is crucial because it opens a new window to these processes, so far unknown due to the lack of such detections on Uranus. The comparison of Uranus polar auroras with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where H3+ emissions have a short life that smooths the variability of UV emission, Uranus' brightest infrared emissions do not necessarily coincide with the brightest ultraviolet emissions of the other planets. This unique aspect of the polar lights of Uranus provides valuable information for the study of exoplanets, especially for the worlds of warm ice giants. The study delves into the unusual hotspots of Uranus observed near the latitudes of the UV aurora borealis. These points, analyzed in terms of temperature, column density, and total emission, suggest that the increase is not caused by temperature, but by greater ionization, probably due to polar auroral activity. The polar lights play an important role in atmospheric heating, and, on Uranus, the increase in H3+ emissions associated with these auroras suggest their participation in atmospheric processes. By studying these unique phenomena, we obtain a deeper understanding of similar processes in different planetary environments, which enriches our knowledge about how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the search to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas that invite more detailed exploration. Recent investigations, including a new analysis of the Voyager images, have revealed that the two planets actually have similar shades of greenish-blue color, which radically changes our ingrained beliefs. Uranus and Neptune share many common characteristics. They are approximately the same size, the same mass, and are surrounded by deep atmospheres of comparable materials. However, for a long time, it was thought that their appearance was quite different. This error has now been corrected, and both planets are shown in their real colors, largely influenced by the methane layer of their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar ice giants. The potential objectives of the mission range from the study of the unique magnetic field and the complex ring system to the investigation of atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the mission of the orbiter and the probe of Uranus has been elevated to the highest priority for the flagship mission of the NASA within the Decennial Survey of Planetary Science 2023 to 2032. Future launch windows are available between 2030 and 2034. Key scientific objectives will include a detailed analysis of the unusual inclination of the axis of Uranus and its effect on the climate and the weather patterns of the planet climate and the weather patterns of the planet. The mission will also be able to study the intriguing phenomenon of infrared auroras and their role in atmospheric heating, providing a comparative study with other planets. The study of Uranus and Neptune will also provide valuable information on planetary evolution and dynamics, and will help us understand why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, which allows methane haze accumulation. This can tell us a lot about the ice giant's atmospheric processes. While we await a future mission to Uranus, we find ourselves on the threshold of discoveries that could redefine our understanding of the solar system. The exploration of this distant ice giant will not only reveal its mysteries, but also expand our knowledge of planetology as a whole, shedding light on the complex panorama of our cosmic home. For years, there has been a concept that challenges the laws of physics as we know them, a dream that has given rise to countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could allow us to travel great distances in space faster than light. Imagine a journey in which the limitations of time and space yield to the power of human ingenuity, where the farthest corners of the universe suddenly become accessible. This is not just science fiction. It is a puzzle that scientists have been trying to solve for decades, since the physicist Miguel Alcubierre proposed a theoretical model in 1994. The model of Alcubierre, a bold combination of imagination and the theories of Einstein, offers a way to curve the fabric of space-time. But what is behind this bold idea? Is it just a fantasy, or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and advances that surround the warp drive, from the mysterious nature of negative energy to the problem of the event horizon. So let's dive into the depths of one of the most intriguing scientific quests of our time, the search for the warp drive. Science or fiction in the heart of Mexico City, in the middle of the hustle and bustle of urban life, a young mind was fascinated by the mysteries of the cosmos. We are talking about Miguel Alcubierre, born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and took him to the We are talking about Miguel Alcubierre, born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and took him to the prestigious University of Wales, where he delved into general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a revolutionary discovery that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's analyze the Alcubierre engine. Let's imagine a spacecraft that does not move through space in the usual sense, but exists inside a space-time bubble. This bubble, or warp bubble, is the key to the Ailery concept. According to Einstein's general theory of relativity, massive objects distort the fabric of space-time. Alcubierre hypothesized that if we could manipulate space-time in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing it forward, while behind it the space expands, pushing from behind. Inside this bubble, the spacecraft remains stationary, But as the bubble moves, the ship can travel faster than light without violating the laws of physics. This idea does not involve moving the spacecraft at high speed, but it is about moving the space around it. It is like putting a surfboard or a spacecraft on a wave, a warp bubble, and letting the space-time ocean carry it. However, the Alcubierre model is not simply a manipulation of space, but requires exotic matter with negative energy to stabilize it. This exotic matter is one of the many theoretical obstacles that scientists face when trying to turn the Alcubierre engine from a fascinating theory into reality. As we delve into the practical aspects of the Alcubierre engine, we face challenges that stand between theory and reality. The first of these is the scale of energy and mass required. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably enormous amount far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. A remarkable achievement was when physicist Chris van den Broek proposed modifications to the shape of the warp bubble. These adjustments drastically reduced the energy requirements to approximately the mass of 3 suns, a colossal amount, but a significant step from the original estimates. The second major obstacle is the need for exotic matter and negative energy in the Alcubierre model. This exotic matter is crucial to stabilize the warp bubble and make it work as intended. Negative energy is a peculiar and controversial concept. It is a concept of physics that can distort the very structure of space-time. It is not just the absence of energy, but a real physical quantity with negative characteristics. In the context of the Alcubierre engine, negative energy counteracts the effects of normal positive energy, creating conditions for the existence and stability of the warp bubble. Negative energy in the context of the Alcubierre engine is, without a doubt, a complex concept and somewhat difficult to understand in physics, and it is important to distinguish it from more familiar concepts such as gravitational potential energy in classical physics. The concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, such as a planet, is considered negative because work is needed to move the object from the source of gravity to a point where this energy would be zero, for example, to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, the negative energy needed for anti-gravity propulsion is different. In this context, negative energy refers to a hypothetical form of energy whose energy density is less than zero. It is not just an accounting tool or a wave that describes the potential energy in a gravitational field, but a real physical substance or field with exotic properties, such as a repulsive gravitational effect. This type of negative energy is not something we observe or understand well in the context of known physics. However, the existence of negative energy, and by extension, exotic matter, remains a topic of intense debate and speculation in physics. Although phenomena, such as the Casimir effect, suggest the possibility of negative energy under certain conditions. Harnessing it to the scale needed for the warp drive is a challenge. These challenges, the enormous energy requirements and the need for exotic matter, underscore the monumental task of transforming the Alcubierre engine from a theoretical model into a practical reality. They not only represent technological obstacles, but also fundamental questions about the nature of the universe and our ability to manipulate its basic forces as we move toward warp drive technology. We face another obstacle known as the horizon problem. This problem lies at the heart of the Alcubierre engine design and poses serious issues for its practical application in astrophysics. The horizon often refers to the limit beyond which events cannot affect an external observer. The most famous example is the event horizon of a black hole, the point of no return. Beyond this horizon, the gravitational pull is so strong that nothing, not even light, can escape. Similarly, in the Alcubierre engine, the horizon is the boundary of a warp bubble. Inside this bubble, the spacecraft is isolated from the rest of the universe, just as the interior of a black hole is isolated from the outside world by its event horizon. The horizon problem arises from the unique structure of the warp bubble itself. In the Alcubierre model, the spacecraft is located in a region of the space-time plane surrounded by a warp bubble that compresses space in the front and expands in the back. This manipulation of space-time allows travel at speeds greater than that of light, but with a critical limitation. It isolates the spacecraft from the rest of the universe. Imagine being inside this warp bubble. The very mechanism that allows you to travel great distances in space also prevents you from controlling the ship or interacting with the outside world. Communication signals, navigation commands, and even visual observations are impeded by the boundary of the bubble. The passengers and the crew will not be able to control the ship, correct its course, or stop the trip once it has started. The implications of the horizon problem are profound. It implies that a warp-powered spaceship would be traveling on a one-way, uncontrolled trip. This raises practical questions about the use of such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with objects or adjust our path to cope with unforeseen circumstances? In addition, this problem implies the need for a pre-established infrastructure, similar to an interstellar highway, with mechanisms to create, control, and steer the warp bubble from the outside. This requirement adds another layer of complexity to the already difficult task of making warp propulsion technology a reality. Although the horizon problem represents a major engineering challenge, it is important to recognize that it does not invalidate the fundamental scientific validity of the concept. In theory, the principles underlying warp propulsion remain plausible within the framework of general theory and validates the fundamental scientific validity of the concept. In theory, the principles underlying the warp engine remain the same and plausible within the framework of the general theory of relativity. As we delve into the complexities of the warp engine, we encounter another major problem: radiation. This problem is twofold, as it involves both the accumulation of radiation at the front of the warp bubble and the potential effects of Hawking radiation within the bubble itself. First, consider the radiation that accumulates at the front of the warp bubble. As the bubble moves through space at a speed greater than that of light, it inevitably encounters interstellar particles and cosmic radiation. These particles and the radiation, unable to pass through the warp bottle, accumulate near its front. Such accumulation poses a significant risk when a warp bubble slows down or stops, as the accumulated radiation and particles are released in a burst of energy. The intensity of this release could be catastrophic, endangering not only the spacecraft and its passengers, but also potentially damaging any nearby objects of the destination moving within the warp bubble. We encounter the second aspect of the radiation problem: Hawking radiation. This theoretical radiation, predicted by Stephen Hawking, arises from quantum mechanics near the edges of black holes. In the context of the Ailery drive, the intense deformation of space-time around the edge of the bubble could create conditions similar to the event horizon of a black hole, potentially generating Hawking radiation. This radiation could have harmful effects on passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are profound. Not only do they pose serious engineering and safety challenges, but they also raise questions on the feasibility of long-duration travel using the Alcubierre engine. Ensuring the safety of passengers and the integrity of the spacecraft against these radiation hazards is a critical area that requires further research and innovative solutions. It is a challenge that requires ingenuity and a deeper understanding of the interaction between quantum mechanics, the theory of relativity, and the harsh reality of space travel. When we turn to the current state of research in warp propulsion, we find ourselves in the midst of scientific research. In recent years, numerous articles and papers have appeared, opening new paths in this field. A notable advance is the work of physicists who revised the energy requirements of the Alcubierre engine, based on previous advances that significantly reduced the estimated energy requirements. Recent articles have proposed several methods to optimize the geometry of the warp bubble further. These improvements aim to make energy requirements more feasible, approaching the realm of possibility. Researchers such as Harold White, who has played a fundamental role in experimental work on the feasibility of warp bubbles and the manipulation of space-time at NASA's EagleWorks laboratories, have made significant contributions in this field. Another area of research is the exploration of alternative theories that could circumvent some of the limitations of the Al-Kubari thruster. For example, some physicists are exploring the possibility of using solitary Solon waves, which retain their shape while traveling at a constant speed, as a basis for creating stable warp bubbles without the need for negative energy. There is also growing interest in the role of quantum mechanics in the physics of the warp engine. Researchers are delving into the quantum aspects of space-time and how they might affect the mechanics of the engine. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the bubble. Recent theoretical advances also include the study of the effects of warp engine technology on causality and the structure of space-time. These studies are fundamental to addressing potential paradoxes and time travel scenarios, and to ensuring that the concept remains based on physical laws as we know them. Little by little, the dream of warp propulsion technology is getting closer and closer from the pages of science fiction to the realm of scientific possibilities, driven by the tireless efforts of researchers around the world. As we reflect on the future of warp propulsion, we find ourselves at a crossroads of assumptions and possibilities. The realization of warp propulsion, a concept previously limited to the realm of science fiction, depends on several key advances and discoveries. First, it is necessary to address the theoretical problems associated with warp propulsion, which includes finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. Advances in areas such as quantum mechanics, exotic matter, and energy manipulation are fundamental to turning these theoretical possibilities into practical reality. Beyond the scientific and technical obstacles, the advent of warp propulsion technology brings with it many ethical and practical considerations. The ability to travel at unprecedented speeds across great distances in space would revolutionize exploration and open new horizons for humanity. However, great power comes with great responsibility. The ethical implications of such technology must be considered. This includes the potential impact on space ecosystems, the responsibility to explore and possibly interact with extraterrestrial life, and equitable access to the technology among nations and peoples. In practice, warp propulsion technology could lead to new methods of resource utilization, new ways of conducting scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space, moving from exploration to habitability and utilization. For now, we look forward to a future in which the stars are not just points of light, but destinations within our reach in the night sky. The future promises unexplored territories and unprecedented exploration, inviting us to continue our quest for knowledge and discovery in the shadowy depths of our solar system. Beyond the last known gas giant lies a world shrouded in intrigue and mystery. Pluto, once considered the ninth planet, now occupies a separate category at the center of heated debate and scientific curiosity. For decades, Pluto continued to be a blurry stain, a distant point at the limit of our vision. It was a world waiting to be discovered, keeping its secrets in the cold, dark depths of space. In the dawn of the 21st century, an unprecedented and ambitious mission began. The New Horizons spacecraft embarked on a journey of 1 billion miles to explore the cold frontiers of Pluto. What it discovered was astonishing in its diversity. Imposing mountains of ice, enormous glaciers of nitrogen, and a legendary Tome Regio, with a heart shape so big it can be seen from space. But these discoveries are only the beginning. Join us on this journey to the icy depths of the outer solar system, where a dwarf planet waits to tell us its story. At the beginning of the 20th century, the search for the ninth planet, the mysterious Planet X, captivated the astronomy world. The search was not limited to adding another name to the list of planets, but it was about understanding the invisible forces that gave shape to the orbits of the then already known acquaintances around us. At the center of this search was the LEL Observatory in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on a meticulous journey through space, armed with a telescope and photographic plates. Tombaugh set out to examine the night sky inch by inch in search of an elusive planet that had eluded detection. On a night in February 1930, Tombaugh's diligence paid off. Among the countless stars, he spotted a moving object, a small point of light different from everything he had observed before. It was Pluto, a distant world that received the name of the Roman god of the underworld, a discovery that would change the limits of our solar system. With the passage of decades, the Hubble Space Telescope brought us closer to Pluto than ever. Launched into orbit in 1990, Hubble's powerful lenses pierced the veil of distance that separated us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a simple bright point into a world with distinctive characteristics. These images from Hubble laid the foundation for a more detailed study. They showed the complex surface of Pluto, marked by variations of brightness and color, hinting at a dynamic world waiting to be explored. An odyssey of discovery that began with a simple flickering point on a photographic plate has taken us to the threshold of a new frontier. Pluto, once a mere curiosity in the confines of our solar system, was about to reveal its secrets thanks to a tireless search for knowledge and an implacable spirit of exploration. 5, 4, 3, 2, 1. We have ignition and liftoff of the NASA New Horizons spacecraft on a decade-long mission to visit Pluto and beyond in January 2006. Humanity embarked on another of its most ambitious journeys. New Horizons, a spacecraft no bigger than a grand piano, was suspended in the immensity of space, heading to a world barely visible to the human eye. Its mission, to unveil the secrets of Pluto, a mysterious dwarf planet located in the outer reaches of our solar system. When New Horizons rose towards the sky, it carried with it the aspirations of countless people who had dedicated years to that moment. The journey was a marathon of cosmic proportions that lasted for almost a decade and more than 3 billion kilometers. With precision, it traced a route through the void, guided by the gravity of the celestial bodies in its path. In 2015, after 9 long years, as New Horizons approached its distant destination, the entire world watched with great expectation. The first images were simply revolutionary. Pluto, which before was only a point of light even with the most powerful telescopes, now looked like a world of mountains, valleys, and plains. The visible landscape was surprisingly varied. Mountains of ice, some as high as the Rockies, rose proudly above the surface, their peaks wrapped in a blanket of methane snow. Sputnik Planitia, a plain of nitrogen ice, extended throughout the dwarf planet, its surface shaped by a complex pattern of ridges and depressions. Among the most surprising discoveries are the indications of geological activity. Pluto, which for a long time was believed to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice flowed slowly through the landscape, and the indications of cryovolcanoes indicated that this distant world was not as inactive as it was thought. New Horizons jumped into the unknown and bridged the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes, but a dynamic world full of surprises and beauty waiting in the confines of our solar system. It was only the beginning of a new chapter in our understanding of the cosmos. The extension of rugged landscapes of Pluto houses one of its most fascinating characteristics. The Sputnik Planitia, an enormous glacier with a heart shape, is not only a striking visual reference, but a geological wonder that has changed our way of thinking about this distant world. The origin of Sputnik Planitia is a story of cosmic forces. It is believed that this vast basin, which extends more than 650 miles, was formed by the impact of an enormous celestial body, an event that changed Pluto's surface and possibly its entire geology. The basin was filled with diverse gases, mainly nitrogen, creating a smooth and reflective plane that contrasts strongly with the surrounding topography. The surface of Sputnik Planitia is shaped with a complex pattern of convection cells, each the size of a country on Earth. These cells are the surface manifestation of the ice in slow motion, stirred and flowing in response to the faint heat coming from Pluto's interior. This process, similar to that of a lava lamp, shows that Pluto is far from the inert and icy world that we once imagined. More mysteries are hidden under the icy facade of Sputnik Planitia. The uniform distribution of mass in this region, obtained from spacecraft measurements, suggests the presence of a denser layer below the ice. Scientists speculate that it could be an underground ocean. It is possible that this deposit contains liquid water isolated by the ice crust that covers it. Among other discoveries, scientists have also found that Pluto has an atmosphere that floats above its icy surface, as thin and fragile as an atmosphere can be in the cold confines of the solar system. Composed mainly of nitrogen, with traces of methane and carbon monoxide, this fine veil provides clues to understanding one of the planet's most mysterious processes. The planet is more mysterious. The structure of the planet's atmosphere does not meet initial expectations. When New Horizons flew by, it found an atmosphere that extended hundreds of kilometers above the surface, much more extensive than expected. This thin atmospheric layer is stratified and presents a complex interaction of gases that scatter and refract sunlight, creating a hypnotic blue tone that resembles the sky of the Earth. Since the orbit of Pluton around the Sun is different from that of any other planet in our solar system, with an orbital period of 248 Earth years, something unimaginable. Each season on Pluton can last decades. Its trajectory is markedly elliptical. It is much closer to the Sun in perigee than in aphelion, and its axis is inclined at an angle of 120 degrees, which gives rise to extreme seasonal variations on its surface. As Pluton approaches its perihelion, the heat from the distant Sun, although weak, is enough to cause a remarkable transformation. The surface, composed of nitrogen, methane, and carbon monoxide, begins to sublimate, a process by which these ices pass from a solid state to a gaseous one without going through an intermediate liquid state. This sublimation is more pronounced in the regions exposed to the weak but constant sun, which causes an increase in atmospheric pressure, since the gases previously trapped in the ice are released to the outside. This degassing thickens Pluton's atmosphere, making it more substantial during these warmer periods. The atmosphere expands, rising hundreds of kilometers above the surface, far more than during the colder periods. This expansion is uneven and influenced by Pluton's topography and the composition of its ice, creating a complex and dynamic atmospheric system. As Pluto continues its long journey away from the Sun and toward more distant parts of its orbit, the atmosphere is undergoing a dramatic turn. Gases that once thickened it now cool and condense, falling back to the surface in the form of a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining characteristic of Pluton's climate. The climate of Pluton changes its surface over the centuries. The position of ice and steam throughout Pluton's long year paints a portrait of a world in constant motion, far from being a frozen and static wasteland. Pluton's surface is a dynamic environment that reminds us of the active and changing nature of even the most distant members of our solar system. Another exciting discovery about Pluton's atmosphere is its escape rate. Unlike the strong magnetic fields and gravitational poles that protect the atmospheres of the larger planets, Pluton's weak gravity allows much of its atmosphere to escape into space. This atmospheric escape contributes to the tail of ionized gas, an invisible wake similar to that of a comet that Pluton leaves in its wake as it orbits the Sun. This leak is not a constant and smooth flow, but a complex interaction with the solar wind, a stream of charged particles emanating from the Sun. When these particles collide with the escaping atmospheric gases, they create a dynamic and ever-changing environment around Pluton, a miniature magnetosphere in which the drama of solar in planetary forces unfolds. From Pluton's dynamic atmosphere and unique climate, we move on to its largest moon, Charon, and discover relationships and landscapes that change the very definition of celestial bodies in the outer part of our solar system. Charon, Pluton's largest satellite, orbits in synchronized motion with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It is a whole world full of geological wonders and a unique history that is intertwined with that of Pluton. When New Horizons flew by Charon, it saw a landscape of canyons so deep and wide that they could easily swallow parts of Earth's Grand Canyon. These abysses extend across the satellite's surface, telling a story of geological upheaval. The mountains, which rise dramatically against the lunar surface, reveal a dynamic history, with their peaks casting long shadows over the valleys. The origins of Charon's dramatic topography lie in its past, marked by internal processes and possibly cryovolcanic activity. As Charon cooled and compressed over millions of years, it split, giving rise to vast canyons. At the same time, the mountains may have formed from tectonic activity, as Charon's surface flexed and broke, pushing flexion and breakage of the moon's surface, pushing some areas upwards and raising peaks. The interaction between Pluton and Charon is a kind of gravitational ballet in which both bodies are locked in a synchronized orbit, meaning that Charon always faces Pluton and vice versa, a phenomenon known as tidal locking. Unlike most moons, which orbit around their planets, Pluton and Charon orbit around a point in space between them known as the barycenter. This unique arrangement challenges conventional definitions of planets and moons, suggesting a binary system in which both bodies are companions in their celestial tandem. This gravitational association extends beyond Pluton and Charon, affecting the orbits of Pluton's smaller moons, Styx, Nix, Kerberos, and Hydra. Charon's presence stabilizes these smaller satellites, which maintain the complex balance of the system. The dynamics of this solar system provides us with valuable information about the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kuiper Belt, Pluton stands as a sentinel on the edge of our solar system. This region, a vast cluster of icy bodies extending beyond Neptune's orbit, is a vestige of the primitive solar system and contains the keys to understanding the formation and evolution of our cosmic neighbor. Pluton, once believed to be the ninth planet, has found its relatives among the vast number of objects in the Kuiper Belt, or KBOs, from the dwarf planets Haumea and Makemake to smaller and lesser-known bodies. Each KBO has its own story that contributes to completing the picture of the solar system. The varied landscape of Pluton, from plains of nitrogen ice to towering mountains and dynamic atmospheres, reflects the complexity and diversity of the landscape of the Kuiper Belt. The Kuiper Belt is a window to the past, a frozen archive of the solar system's birth. The objects that compose it, including Pluton, are vestiges of the era of planetary formation. Having not been touched by the sun, its composition, ice mixed with rocks, gives an idea of the materials that abounded in the primitive solar system and allows us to understand the processes that led to the birth of the planets. The exploration of Pluton and its neighbors in the Kuiper Belt has far-reaching implications for our understanding of the solar system. Each mission, such as the New Horizons probe's flyby of Pluton, unveils layers of mystery and reveals the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to consider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluton's position in the Kuiper Belt emphasizes the interconnection of celestial bodies, from the smallest piece of ice to the largest gas giant. The dynamics of the Kuiper Belt, with its resonances and orbital interactions, influences the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting Neptune's environment. However, the New Horizons exploration did not end there. It ended there. After its historic flyby of Pluton, it continued its path towards an object of the Kuiper Belt, which it met on January 1, 2019, marking the next milestone in space exploration. Iroko, which resembles a clay snowman, demonstrated the smooth fusion of two primordial objects, offering an unprecedented vision of the basic components of the early solar system. The story of Iroko's formation is a testament to the slow and gentle processes that dominated the outer reaches of the early solar system. The large lobe called Bennu is not a unique formation, but a cluster of a dozen rocks more than 3 miles wide crowded around a central core. This cluster refutes previous ideas about high-speed collisions in planetary formation and suggests, instead, a gradual fusion at speeds less than a dozen feet per second. This intricate interaction between two lobes that lose angular momentum and merge smoothly paints an image of a patient cosmos, where the basic components of the planets come together in a celestial dance of gravity and time. Looking ahead, the horizon of solar system exploration is plagued with potential concepts for the upcoming New Horizon missions. The missions are already awakening the imagination of scientists and engineers. One of them foresees an orbiter capable of mapping the surface of Pluton with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by the axial tilt of Pluton. The project, inspired by the legacy of Cassini, proposes to use the gravity of Chan to create complex orbital trajectories around Pluton, which would allow a comprehensive study of the dwarf planet and its satellites. These missions could use electropropulsion, replicating the success of a NASA Dawn mission, and could go beyond the Pluton system to explore new frontiers in the Kuiper Belt. New technologies, such as direct fusion thrusters, promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report titled Fusion-Enabled Pluto Orbiter and Lander, Pluton Orbiter and Lander Powered by Fusion, from the NI Program of Innovative Advanced Concepts of NASA, describes a mission to Pluton with a direct fusion thruster that uses a fusion reactor. A 1,000 kilograms orbiter could reach Pluton in just 4 years, more than twice as fast as New Horizons. These promising propulsion systems could significantly shorten travel time, opening new possibilities in the exploration of the distant worlds of our outskirts as we travel through the vastness of space, exploring distant worlds and discovering their secrets. Our understanding of the cosmos continues its evolution. The story of Pluton, from its discovery to the present day, is a vivid reminder of the dynamic nature of science and our attempts to categorize the universe around us. Pluton's unique orbital interaction with Neptune adds another layer to its fascinating history. During its 248-year orbit around the Sun, Pluton appears closer to the Sun than Neptune for a brief period, challenging the view of its position as the ninth planet. This crossing of orbits, when Pluton and Neptune change places, occurs due to the elliptical trajectory of Pluton's orbit and its inclination relative to the plane of the solar system. Despite this temporary change, Pluton's overall trajectory ensures that there is no risk of collision with Neptune due to their shared orbital resonance. The long debate about Pluton's planetary status has sparked discussions and controversies that go far beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of planet in our solar system, leading to the reclassification of Pluton as a dwarf planet. This moment not only marked a turning point for Pluton, but also catalyzed the reclassification of other celestial bodies. The story of Pluton is closely linked to the Kuiper Belt, a region full of objects that blur the lines between planets, moons, and smaller celestial bodies. The study of Pluton and its neighbors makes us think about the wide range of characteristics that celestial bodies can possess, from their atmospheres and geology to their orbits and interactions on the great canvas of the cosmos. Each thread, from the smallest asteroid to the most powerful gas giant, plays a fundamental role in the story of our solar system. Now that we are on the threshold of new explorations, the legacy of Pluton and the knowledge acquired in the Kuiper Belt serve as beacons, guiding us toward the deeper understanding of our place in the universe. Rethinking our cosmic neighborhood is not just about the labels we assign, but about embracing the diversity and complexity of the universe.